I just welcome to this afternoon session of our second day of our 10th anniversary conference. I hope that you've had the opportunity to have something in your stomach, and I will pass the word directly to the moderator, Professor Sherif Dridi. So you have the word from moderator.
Thank you very much, Daniel. I will start by the presentation of our colleague, Dr. Shahidul Alam, who received his BSc degree in physics from University of Chittagong, Bangladesh. Then he obtained his MSc degree in electronics engineering from Bremen, Germany. During his master's studies, he worked on organic electronics in Professor Wagner Grau at Jacobs University, Bremen. In 2015, he joined Professor Schubert's Grau at the Center for Energy and Environmental Chemistry, Friedrich-Schiller University, Jena. He received his PhD in 2020 from the Faculty of Chemistry and Earth Sciences, Friedrich-Schiller University, Jena, under the supervision of Dr. Harald Hoppe and Professor Ulrich Schubert. Currently, he is working on as a postdoctoral fellow in Jena, and his research interest is charge transport in organic semiconductors, device performance and stability of solution processed polymer solar cells. He will give a talk entitled Improvement of Donor Crystallinity and Phase Separation in Organic Solar Cells based on anthracene-containing PPE-PPV composites. Yes, Doctor.
So thank you very much for the kind introduction. So I would like to share my screen. So here it is. So do you see my screen now?
Yes, perfectly.
Okay, good. That's good. So good afternoon, everyone. And it was my pleasure to have a talk in the nice event. And I would like to thank the organizers to give me the opportunity to discuss some of my results that I was working on during my PhD study. And I have finished my PhD last year under supervision of Dr. Harald Hoppe, and my PhD studies was funded by a DFG project where I have been working for 4 years or 5 years in a project collaboration with Professor Daniel Egbe. So next half an hour, I am going to show you some of the most outcome from the project. Although the title of my topic, the talk is the improvement of donor crystallinity and phase separation in organic solar cells based on anthracene-containing polyphenylene ethylene, polyphenylene vinylene. However, I have slightly modified my talk, and I will show you also some other data at the end of my talk. So first, I would like to show you the outline of my talk, and I'll give you a short motivation and then some experimental details and the most outcomes and results and discussion. And at the end, I will summarize my talk. So as a motivation, I think I do not need to tell in details because the talk was, or the motivation was explained by the last talk in the morning session by Dr. Christian Gessner, and he explained very nicely all the details to get the aggregation and crystallinity, and he did all these complicated stuffs like binary blending, ternary blending of the amorphous and semicrystalline polymers, and also some blending of the solvents and so on. But here I am going to show you a simple approach that we can do or induce the aggregation in the solution by adding some kind of anti-solvent or orthogonal solvent. And this I found very motivational, that when we add some kind of orthogonal solvent into the host solvent, then we can induce the aggregation of the polymer donor in the solution. And this solution can be transferred into blend films, and where we can see the effect of aggregation in bulk heterojunction organic photovoltaic, and which finally enhance the charge generation, transport, and the extraction due to the morphological improvement. So in the experimental, I have prepared the solar cells in a conventional architecture. In the left-hand side, you can see the layer stack. The solar cell device was built on ITO-coated glass substrate with an whole transport layer, which is the P.PSS, and the photoactive layer, and then finally the cathode was deposited as 150 nanometers of aluminum. And for this polymer that we consider one statistical copolymer synthesized by Professor Daniel Agbe, and which is known as the AnE-PV start. And we combine this with PCBM 60. And the blend ratio was used, this was the optimized blend ratio that we used 2:3, and solvent was, host solvent was the 1:1 ratio of chlorobenzene and chloroform. So, and then by adding some fraction of methanol into the host solvent, we can see on the right hand side from the graph that the absorption and photoluminescence was slightly increased by adding the methanol, which is the red curve. And then absorption, we can see this, that is related to the larger polymer fraction or alignment, or more alignment of the same with the respect to the substrate, or we can induce as the domain size larger. And also with the photoluminescence is related to the more extended phase separation, that respectively larger polymer domains. And this effect we can also see from the morphology by AFM measurement, and we can see on the left hand side is the phase image, and on the right hand side the topographic image for the pristine blends and the anti-solvent or methanol added blend. And this we can also, in order to have a better charge extraction, that we want to have an optimal morphology to have the better charge generation and transport. And then moving to the IV characteristics of the solar cells, that we can see on the middle graph the dark IV measurement of the pristine device and the device prepared with the methanol as an anti-solvent. And we can see from the reverse direction the slight improvement, there's the reduced current, and we have the, it makes sure that we have in the better blocking behavior in the solar cell, and overall the rectification of the diode is improved due to the vertical alignment. And right hand side we can see the linear the IV characteristics under illumination, and we can see even though there is not so much improvement in the VOC, but very tiny improvement in the current density and also the fill factor. And the current density can be confirmed by the external quantum efficiency measurement, and then we can see in the table that the overall power conversion efficiency for the methanol added device is improved from 2.83 to 3.3%. And looking at the electroluminescence spectra, it's pretty interesting. And then if we look at the spectra from 900 to 1100, and we can clearly see the CT emission is increased compared to the polymer emission, which is close to the 600 nanometer, and due to the improved access of the interfacial area between polymer and the acceptors, and which is tells us the charge carrier moves via improved percolation, and the charge transport within the more ordered phase also improve the selective injection that we have seen from the IV characteristics of the solar cells. So also I have determined the charge carrier mobility from the both kind of devices in hole only device, which was prepared in architecture with symmetric structure and two metal electrode on both sides of the films, and with two hole transport layer, which was molybdenum oxide. And by fitting the dark IV characteristics, and we can see there is an improvement in the whole mobility when we added a little amount of methanol into the blend solvents. And in another studies with EMNA from Tunisia, and there in another studies we have also shown that not only the methanol but also the isopropanol can improve the power conversion efficiency of the solar cells as well as the charge carrier mobility. And here we have shown a nice study with the temperature dependency also, and with the whole mobility and the power conversion efficiency improved by the processing temperature. So the processing temperature is the solution was at first heated up to 85 degrees centigrade, and then we let the solution to cool down, and while cooling down we processed the films at the respective temperature from 55 degree down, and we went down to 15 degree centigrade. And we can see that when during upon cooling the solvents, the film most crystallized and gives us the better photovoltaic performance, and also the improved the whole mobility. So to summarize my first part of the talk, that I can tell that is the orthogonal solvent or anti-solvent additive can induce the aggregation of the polymer donor in solution that could be successfully transferred into blend films in organic photovoltaic. And also the methanol additive to the standard solution or host solution lead more substantial and better ordered polymer domains and more dispersed PCBM phase that confirmed by the increased in whole mobility. And then finally, I can tell that this morphological improvement results in an enhanced charge generation, transport, and extraction, as well as an impeded recombination of free charge carrier, leading to an overall improvement of the solar cells parameter. Now I'd like to move to the second part of my talk, that we have also combined this AnE-PV start of the polymer with non-fullerene acceptors, and what is the outcome that we have seen. So as a motivation, so the non-fullerene acceptors is nowadays very popular, and because of its stability and the cost and the performance. This is a little bit older, but I think this is still in 2021 or recently, this the non-fullerene acceptor based solar cells has already reached to 18% recently. So that is why we were interested to combine some non-fullerene acceptor into the statistical copolymer with an EPV start. And to do that, we combine this statistical copolymer with plenty of non-fullerene acceptors with the PDI based, which is PA2, DAP2, and TAP2, and also the most commonly used non-fullerene acceptor ITIC. And we also compared those with the PCBM as a reference. And this is the energy level alignments, or there's the or determined by the cyclic voltammetry measurement from all the pristine materials. And on the right hand side we can see the energy level alignments and with all HOMO and LOMO values of the pristine materials. And we can see if even though there is a deviation in the offset between HOMO of the donor and HOMO of the acceptors, however, there is not too much difference in the LOMO offset between the donor and all other acceptor materials, which tells us that energetic point of view, all this combination or the combination of an EPV start with all non-fullerene acceptors should work. So at first I would like to show you the optical characteristics of all those pristine materials and blends, and then first start with the AnE-PV start and PCBM. And we don't see too much differences in the absorption. It's no additional as it is, but interestingly and we can see from the right hand side that in the blend the photoluminescence was quenched by 2 orders of magnitude, and this tells us the proper domain size for the charge extraction. And from the blend we can see there is a little amount of the PCBM emission, but no city state emission was seen. And that tells that there is non-geminate recombination. No geminate recombination. So if we move to the AnE-PV start ITIC, in the left hand side from absorption, we can see there is an extended absorption. It's the optical properties of the ITIC, and this also reflected in the blend. Interestingly, on the right hand side, we cannot see any polymer emission because it's fully quenched, but we can see there's an emission from the blend, and this could be the emission from the pristine ITIC or maybe the CT emission from the blend. So if we look at the PDI based, one of the PDI based non-fullerene acceptors, there is no substantial gain from the absorption, and the donor and acceptor is completely quenched, but we may be seeing this is an CT emission, and this tells us that there is a very fine or intimate mixing between 2 components. And an EPV start with DAP2, and we can see again there is an extended absorption from the left hand side, and from the photoluminescence that the donor materials is completely quenched, and from the blend either it from the pristine or from the acceptor materials, or could be the CT emission. And tiny shift from the blend emission may be due to the molecular rearrangement or the CT emission. If we look at the last PDI based non-fullerene acceptor in combination with an EPV start, there is an extended absorption observed. However, there is both materials, the donor is completely quenched, and very rough signal from the pristine non-fullerene acceptor, but there is a signal from the blend materials, and either could be from the CT emission or from the DAP2 fullerene acceptors. So in this case, the charge transport remains questionable, and maybe we don't have the charge transfer, but maybe a charge transfer is the energy transfer. And looking at the morphology again by AFM measurement, and we can see from the top two pictures the AnE-PV start PCBM and AnE-PV start ITIC, and in those cases there is a slightly larger average grain size which may associate it with the AnE-PV start. However, from the lower pictures with the AnE-PV start with all other non-fullerene acceptors, there is not the optimal domain size observed, and this might be a problem to have the phase separation. So now looking at the photovoltaic performance, and from the left hand side we can see the dark IV characteristics of AnE-PV start with PCBM and all other non-fullerene acceptors, and we can see this the photovoltaic properties can be observed only from the combination of AnE-PV start and PCBM. However, from all other non-fullerene acceptors gives a kind of an symmetric IV characteristics that tells there is no rectification, no diode behavior, and we can see on the IV characteristics under illumination that all the device are not showing any photovoltaic properties, is the power conversion efficiency is very, very low, whereas the AnE-PV start and PCBM was like showing 3.5% approximately. So this could be the we can conclude that due to the complete polymer was quenched and there was no domain size for charge transport, and maybe potentially energy transfer was happening on those combinations. So to summarize this, that in the beginning I have shown the energy level alignments of AnE-PV start and all other non-fullerene acceptors and also PCBM. And from the energetic point of view, as I said, that all combinations should work. However, we see that except AnE-PV start PCBM, the all other device shows a very bad diode properties and photovoltaic properties, and this might be explained by the complete PL quenching for the AnE-PV start in combination with all other non-fullerene acceptors. And also the optical measurement indicates that there is too fine intermixing between AnE-PV start and all NFAs. So in order to look at deeper insight into the energy level alignments of all those combinations, so here I would like to shortly show you that how the determination of expected and effective band gap of organic semiconductors. So expected band gap is calculated basically from the difference between the HOMO of the donor and LOMO of the acceptor, and those values are often measured by the cyclic voltammetry measurement that also I have shown previously, and from the CV measurement, and people calculate the difference and it is known as the expected band gap. And those measurements normally performed on the pristine or the pristine materials, and then they have the rough estimation of the expected band gap. However, if we are allowed to measure the band gap in the blend films, then what could be the situation? So the situation could be that the band gap in the blend could be smaller than the expected band gap. So, but we call it the effective band gap, and it could be also larger. So this, if we can only be sure if we are allowed to or able to measure the band gap in the blend, which is normally not the case because people normally use the cyclic voltammetry measurement from the different materials. So again, I am going to show you the molecular energy levels from my previous section, and then on the right hand side you can see that if we have the difference or the LOMO and HOMO of the acceptors are lower than LOMO and HOMO of the donor, this is the formed and bulk heterojunction type 2, then we have efficient charge transfer. However, if it is not the case, then it could be the heterojunction type 1. But all the energy levels that were determined by CV measurement that confirm that we have the bulk heterojunction type 2, and this combination should work from their energetic point of view. However, it was not the case. So, and that is why, and here I am going to show you the energy landscape of two special cases. So AnE-PV start with PCBM and AnE-PV start with ITIC.
2
And
minutes,
if
please.
you look at the left hand side on the graph, then we can see that the expected band gap that was calculated from the CV measurement is around 1.39 electron volt. And if you measure, or we measure the band gap in the blend films, which I call it the effective band gap, and which is 1.12 electron volt. That means there is a 270 milli electron volt lower. If you look at the right hand side, that the expected band gap is 1.44 if you determine from the different materials or from pristine materials, and unexpected, even though the expected band gap is 1.44, however, unexpectedly the effective band gap gets larger by 460 milli electron volt. Even though there is a minor differences or almost no differences in the HOMO energy, but there is a shift in the LUMO energy levels, and it's at around 3.54 electron volt.
1 minute, please.
Okay. And to explain and or understand in better that we have determined the city state energies for those two combinations, and on the left hand side we can see on the very right side with the orange line the city state energy for the AnE-PV stat PCBM is larger than the effective band gap, or which also known as the transport gap of the blend, and it's larger. And on the right hand side you can see we can show the consolidated city, or because those cities it is a city state range determined by the different technique, and then this is much smaller than the transport gap or the effective band gap of the blend system. So what we can tell from this to summarize that in one case there is an energy barrier required to get the charge from city state to the transport state, finally in the charge separated states, and in another case there is no barrier, but you have an efficient charge transfer by downhill processes. So now I'm at the end of my talk, and to conclude, that I have in the beginning, I have shown that the introduction of orthogonal solvent in the AnE-PVab PCBM induce the aggregation in the films, and which can be seen also from the photovoltaic behaviors. And in the second part of my talk, I have shown you the PL quenching for the AnE-PV with all other non-fullerene acceptors indicates too intimate mixing that causes strong recombination. And at the final part, I have shown you the charge generation in an AnE-PV ITIC blend may require to overcome an energy barrier or to go into the CT state to the charge separated state with an uphill process. And now I am at the end of my talk, and I would like to thank a number of people. At first, I would like to thank my supervisor, PhD supervisor, Dr. Harald Hoppe, for supervising me or allowed me to work on this project for last 2 years and kept his faith on me and give all the responsibility to continue the project. And also our institute leader, Professor Ulrich Schubert, for giving us the opportunity to work in his institute, and all the collaborator partners, Professor Frederick Lucky from Saudi Arabia, and Professor Daniel Egbe and Dr. Christoph Ulrich to provide the polymers donor materials, and Professor Gregory Welsh from Canada. He provided us the all PDI based non-fullerene acceptors, and Martin Haggard to provide us the ITIC, and Christian Fiebe for the measurement CV, and also one collaborator from Bratislava to give us the advanced electrochemical measurement, Dr. Christian Kessner, because I have learned all those things from him. He was my senior, and all of my co-workers, lab mates, and my co-authors, especially Rico, because he was one of the most we shared a lot of papers as a co-authors. And finally, DFG for funding my PhD, and now I am funded by the Infratech for my postdoc research. And thank you all for your attention.
Thank you very much, Dr. Alam, for this very rich presentation. And I propose to move to the next presentation due to time restriction. The next presentation will be given by Dr. Moufid Radaoui from the University of Tunis El-Manar. He is member of the Laboratory of Advanced Materials and Quantum Phenomena at the Faculty of Sciences of Tunis, University of El-Manar. He studied physics at the Faculty of Sciences of Bizerte, where he was graduated in 2009. He received a doctorate degree from the Faculty of Science of Tunis in 2015. He is assistant professor at the Faculty of Science of GAFSA. His main areas of research is concerned with theoretical and experimental studies of magnetic field effect on the current in organic devices such as OLEDs and OPV. Static and dynamic electrical investigations on polymer solar cells. He focused in particular on the carrier combination and generation to minimize the losses in the organic photovoltaics devices. The talk is entitled Influence of Thermal Annealing on the Performance of Bulk Heterojunction Polymer-Fullerene Solar Cells based on PCBM based nanocomposites. Dr. Radaoui, please. You have 30 minutes.
So thank you very much, Professor. I have introduced myself. So I am Moufid Radaoui, assistant professor at the Faculty of Sciences of GAFSA, doctor of quantum physics, which I graduated in the Faculty of Sciences of Tunis. With a collaboration.
Hello.
Yeah.
What is wrong? What is the noise?
Hello?
There's a noise. There's a noise.
Yes. You remove this apparatus, Radaoui. Yes.
But he has put off his microphone.
Yes, I am in my office. Yeah.
Where are you? Why is this noise?
Can you change the microphone, please?
Can you change where you are sitting? The noise is too much.
Or the PC?
Not now, because of this. Hello?
Yeah, when you the noise, there's a lot of noise.
I don't know. I don't know what's the cause of these noises.
It's from your microphone.
Whenever you put up the microphone, it goes off. So I don't know.
Have you kids?
No, I don't have a kit because I have to every day I use my PC without any kit, so I don't know what's the cause of these noises. Really, I am very sorry for this.
Can you change the PC or the...
Okay, I will try to change.
Professor Sharif, can you move for the next presentation, and we
Yes,
I will ask if it is possible.
Yes, if Professor Harald Hoppe here, please.
Harald, you're hearing us, Harald?
Or Professor Andrea Balducci. Yes.
Harald Hoppe is here. Actually, I'm seeing him. Why he has
If it is possible that Harald give his talk. Yes. Ah, I'm here. Okay.
Yes.
It's not.
can you give you a talk now? Because
Professor Harald Hoppe, I will present your biography, please. Yes, Professor Harald Hoppe received his PhD in 2004 from the Johannes Kepler University Linz, where he started his work in organic photovoltaics by investigation of material and phase morphologies within organic bulk heterojunction bands and their impact on device properties. Thereafter, he built up a research group at Tunis University of Technology. In 2015, he joined the Friedrich-Schiller University of Jena at the Center for Energy and Environmental Chemistry, Jena. His current research interests are materials and strategies for improved solution processing, device performance, and long-term stability of organic photovoltaics, as well as imaging methods for offline and inline inspection. Professor Harald, please.
Yeah, thank you very much.
Yes, you can share your screen. Professor Harald Hoppe.
I think we lost Professor Hoppe now. So maybe he lost connection.
he has to come back.
We'll wait.
He's not from a in bracket third world country where there's no internet connection. so he has to. He's just here in Germany, so I don't see why there should be a problem. At the same time, Moufid, have you succeeded to?
Yes, I obtained a kit.
So can you speak?
No.
Yeah, you can speak now without. Yeah, that's good. So let's continue with Moufid.
Okay.
Let's go back to Moufid. So it's. So you can start your presentation. Share your screen and start.
Is it clear?
Yeah, you can speak. We can hear you.
Okay. Thank you very much. So I am very sorry for this problems, which is out of my responsibility, really. Okay. So I will present a lecture entitled Influence of Thermal Annealing on the Performance of Bulk Heterojunction Polymer-Fullerene Solar Cell based on AnE-PVab. So this work was done in collaboration between the Institute for Organic Solar Cells in Austria and our laboratory of Advanced Materials and Quantum Phenomena at the Faculty of Sciences of Tunis University, Tunis El-Manar. Let's start this lecture by the introduction, and I will show you the experiments which are done during this work. After that, we show you the results obtained, and I will finish by acknowledgements and the conclusions. For this cell structure is sandwiched between two electrodes. The active layer is the AnE-PVab PCBM, which is sandwiched between the ITU-PVab process and the silver, which is covered. For the mechanism of an organic solar cell, first of all, we have an exciton generation from absorbed photon. The exciton dissociation in the donor-acceptor interface. Then we have the electron transport in the acceptor lost in occupied molecular orbitals, LUMO. The electron extraction, the whole transport in the donor highest orbital occupied molecular orbital, HOMO, and we have finally the whole extraction and the molecular recombination. So in solar cell fabrication process, ITU coated glasses were firstly subject to standard cleaning process, bath with deionized water, acetone, and isopropyl alcohol for 15 minutes, and dried with dry nitrogen. Then the pre-cleaned ITU substrates were first treated with UV ozone for 5 minutes. After that, the whole transport layer PVab process was being coated at 3000 ppm on the substrates and then annealed at 140 degrees Celsius on a hot plate for 10 minutes. Afterwards, fullerene polymer blend was coated at between 1000 to 1200 ppm for 20 seconds onto the PVab process barrier layer to prepare 7 devices, samples from E to G. So sample E is for without annealing the temperature, sample B annealed at 100 degrees Celsius, sample C annealed at 105 degrees Celsius, sample D annealed at 110 degrees Celsius, sample E annealed at 115 degrees Celsius, sample F annealed at 120 degrees Celsius, and sample G annealed at 125 degrees Celsius for 10 minutes, and immediately transferred inside nitrogen blood box. The films of the fullerene polymer granules were dried in vacuum at ambient temperature for 30 to 40 minutes. Afterward, top electrodes comprising calcium and silver were deposited through a shadow mask on the blank film by thermal evaporation in vacuum. Finally, the obtained devices were encapsulated with glass by using oscilla UV epoxy. For the measurement, the current voltage measurement of the solar cell devices were performed using EM 1.5G solar simulator and recorded with a Kefli 2400 source measure unit. For the impedance spectroscopy was carried out using HP 4284T LCR meter operated in the frequency range 20 to 10 6 Hz. An obtained voltage of VRMS equal to 20 was applied to the solar cells via 4-point connection, which is given by this picture. So, in this figure, we show the IV characteristics of our current density versus applied voltage characteristics of our structures that have undergone annealing at different temperatures. The devices show the solar cells behavior. The photovoltaic parameters of the various cells are given in this table, namely the open circuit voltage VOC, the short circuit current GSC, the fill factor FF, and current and voltage at maximum power output EM and VM respectively. So in this figure, we show the short circuit current and the fill factor versus annealing temperature. One can see that the GSC and the fill factor increase when the annealing temperature pass from 25 degrees Celsius to 110 degrees Celsius, while they decrease considerably for higher annealing temperatures. So we move now to the open circuit conditions. Under open circuit conditions, we have V equal VOC and G equal 0, and with the assumption that P is greater than S, VOC can be expressed by the expression given in this slide. Under practical conditions, the device exhibits both the combination current and the fusion current. Hence, the value of N normally ranges from 1 to 2. G dark value was measured under dark illumination at 0 dS. So, in this figure, we plot the measured and calculated VOC as a function of the annealing temperatures. In contrast, the measured VOC value were lower than the calculated ones, showing that the calculated and measured VOC values have a similar tendency. So here, the enhancement of the solar cell performance observed for the annealing temperatures below 110 degrees Celsius could be attributed to the fact that annealing the plant leads to more compact nature of the films and the decrease of the surface roughness. Moreover, the highest value of the fill factor obtained for 110 degrees Celsius annealing temperature can be related to an optimal phase separation in the plant. In fact, for the anthracene-containing PPV mixed with PCBM, upon annealing, the grain size slightly decreases and a more compact film is obtained. So the latter result are confirmed by the AF1 morphology presented in our previous work by APA. So in general, VOC is controlled by the splitting between the quasi-Fermi levels of hole and electron populations at the two corresponding charge extracting electrode. Furthermore, the VOC is expected to be determined by both the built-in field and the photo-induced contribution by the electrochemical potential gradient across the observed layer. So here, the maximum value of VOC is equal to 0.81 volt, which is obtained at T equal 110 degrees Celsius. The latter is expected to be in the range of 0.87 volt for the difference between the acceptor's LUMO and the donor's POM. The decrease in VOC for the higher annealing temperature may be due to the creation of the polymer wetting layer in the electron extracting electrode, which results in increased recombination of charge, leading to reduction in the quasi-Fermi electron level. Now we move to the impedance spectroscopy measurement. We show here two figures with two different conditions. For the figure E, we present the Purple plots under short circuit conditions, and for the figure B, we present the Purple plots under open circuit conditions. So here we should mention that under short circuit conditions, the Purple plots demonstrate an increase in the semicircle radius for devices annealed at 25 degrees Celsius and 100 degrees Celsius, indicating a change in the resistive and electric properties of the active layer. So the semicircle already decrease with increasing annealing temperatures from 105 degrees Celsius and above. However, at VOC conditions, we observe that the semicircle already increase with increasing the thermal annealing. So to reproduce theoretically the different results obtained by the impedance spectroscopy, the impedance response can be analyzed using an equivalent circuit based on a resistance, series resistance S standing for contact and wire effects, followed by a transmission line model for organic solar cell, consisting for a transport resistance RT, accounting for electron transport and electron recombination resistance R combination, chemical capacitance, and geometrical capacitance. The electric effect of the cathode contact with the photoactive layer is modeled by a parallel resistance RCO and a capacitance CCO. The impedance model described above contains two characteristic times related to electron diffusion or transit time to diffusion, which is given in this slide, and the recombination time. In addition, the diffusion constant, which describes the electron diffusivity, can be calculated through the relationship dN, also is given in this slide. So from the diffusion constant expression, we can deduce the diffusion length, which is defined as an average distance in which mobile carriers can diffuse before a combination and is related to the diffusion coefficient by Ln, also is given in this slide. In addition, an estimation for the electron mobility is calculated using the Nernst and Stein relationship as μn, which is also given in this slide. So here to fit the
impedance of the Purple plots under short circuit conditions. We simulated the impedance plots with the constant Rs, which is equal 1 ohm, because low series resistance Rs are found that are related to conductive ITU and PPE electrical response, while RCU exceeds Rs by more than 1 order of magnitude at low voltage near 0 volt. For this reason, we have taken also constant in the fitting process RCO equal to 10 ohm. Moreover, according to other works by Belmonte and Sanchez, the chemical capacitance and the contact capacitance are also constant in the fitting process, and consequently, we just varying the recombination and varying the resistance, the recombination resistance and the transport resistance to fit the experimental results. In this figure, we show a good agreement between experiments and theoretical results. So we have extracted the parameters suited to both from the fixed to experimental data, and that are summarized in this figure. So under short circuit condition, we found for all annealing temperatures, the recombination resistance is greater than the transport resistance, and as a result, the recombination arc is determined by the product of the recombination resistance by the chemical capacitance. Moreover, the carrier diffusion length Ln is more than the thickness of the active layer, and it is estimated that Ln equal 1.4 L, because at low applied voltage around 0 volt, carrier diffusion length Ln for good heterojunction is more than the thickness of the field. So from the last table we plotted in this figure the diffusion time and the recombination time as a function of the annealing temperature under short circuit condition under simulated TM 1.5 G. So from this figure, the diffusion time increases from 68 microseconds at 25 degrees Celsius to 70.8 microseconds at 100 degrees Celsius. The same magnitude, the same behavior of the recombination time, which increases from 74.8 microseconds at 25 degrees Celsius to 106.8 microseconds at 100 degrees Celsius. Then rapidly decreases to around 35.2 microseconds at 125 degrees Celsius. So the latter behaviors are similar to the behavior of the recombination resistance and the chemical capacitance, which is given in the previous table. Furthermore, under short circuit conditions, an extended depletion zone occupies a large part of the active layer, which supports the argument that bimolecular recombination plays an important role under these conditions. So now we move to the impedance spectroscopy of the Purple plots under open circuit voltage conditions. So the feats of the experimental Purple impedance plots under open circuit conditions are given in this figure. Both resistors RS and RCO contribute similarly to the total cell resistance at forward bias near VOC. We have taken to reproduce theoretically these experimental results. RS equal RCO equal to 0.1 ohm. Moreover, according to Belmonte et al. And Sanchez et al., the chemical capacitance, the contact capacitance, and the transport resistance are constant in the fitting process. We have taken the chemical capacitance equal to 3 microfarad, the capacitance equal to 5 nanofarad, and the transport resistance equal to 1 ohm. Consequently, we just varying the recombination resistance to fit the experimental data. In this figure, we have shown a good also agreement between experience and theoretical results. We have extracted in this table the parameters cited above from the fixed to experimental data that are. So to conclude, we have studied the photovoltaic properties of solar cells with different annealing temperatures into 2 different conditions at 0V, at short circuit conditions and at open circuit conditions. The saturation current and density and the fill factor increased as a function of annealing temperatures from 25 degrees Celsius to 110 degrees Celsius. From 110 degrees Celsius, the 2 parameters decayed considerably for higher annealing temperatures. The VOC initially increased up to 100 degrees Celsius and it reached a maximum value around 0.81 volt and then decayed considerably for 115 degrees Celsius and above. Under short circuit conditions, we found for all annealing temperatures, the recombination resistance is greater than the transport resistance and we carry the fusion length is more than the thickness of the active layer. However, under VOC conditions, just the recombination rate which affects the fits and the other parameters are similar for all annealing temperatures. We found an effective lifetime of the order of few microseconds, which indicates that the photo-generated carrier gas under bimolecular recombination less. So to see more for this works, we can download our previous work, annealing temperature dependence, and the analysis of the AC response by our team. So for the acknowledgement, I would like to thank Professor Sarsifci, also Professor Daniel, and Professor Marcus Clark-Sharber, Adam, Patrick Dank, and Birgit Powell. So let's drive tomorrow today. Thank you for your attention.
Thank you, Dr. Radaoui. There, just one question.
Yeah.
Otherwise, we move to the invited lecture of Professor Harald Hoppe. Professor Harald Hoppe will give an invited lecture entitled Organic Solar Cells for Agrivoltaics.
Yeah, thank you very much. Again, I just had a crash before. Now I'm trying to share my screen. Now it's possible. So that will be my screen.
Good.
Okay, so can I start?
Yeah, yes.
Okay, thank you. So yeah, welcome to my presentation, and I would like to thank also very much for this opportunity to present some of our work. I have to admit I only have a short section about our own work, which is based on the recently published essay and I made up a few more thoughts around the whole problem. So at first I would like to thank my co-authors Rico Meitzner and also Professor Ulrich Schubert, who contributed to this work. And let's get started. So this is the outline of my presentation. At first, I will provide you some motivation and introduction. And then I will show some existing examples of agrivoltaics that I did never develop, but which are already out there and are good to study. And then comes basically our suggestion, which is the perfect match for agrivoltaics to be found in organic solar cells. And then I come to summary and conclusions. So this is my motivation introduction. The question I would like to put up here is food production still profitable? And maybe we also have to ask from our side how far we need to go to make it profitable. Yeah. So there are several issues here. I do not want to get into big depth for all of them, but I think I clearly placed them here. And so it is an issue that we are not only, let's say, dealing with in the Western world. I think it's a worldwide issue, or has become a worldwide issue. So why is food production the interesting question here at the moment? Yeah. Well, it has to do with farmers, and basically worldwide, the food production relies on subsidies to balance for the true costs. And that is actually a huge number. You will find various information about that easily in the internet. For example, here we have the number of about 700 billion, and just 1% of the 700 billion US dollars a year given to farmers is used to benefit the environment, the analysis found. Much of the total instead promotes high emission cattle production, forest destruction, and pollution from the overuse of fertilizer. Yeah, and this is of course an issue we may also not lose out of sight. But the question is why we at first get there, yeah? And so some of the problems that are actually becoming obvious is that farmers have to sell their products below the actual production costs. Here is one example right from Germany on the milk prices. And as you see here consistently over the last 10 years and more, the milk prices were and still are clearly below the production costs. So basically you make minus when you're selling milk, producing and selling milk in Germany. Very nice. I get the phone call right now. Anyhow, so that's one of the reasons why there are the subsidies. So what else is going on? Yeah, actually farmer protesting around the globe. Yeah. You see here, they are protesting in India and they are protesting in Berlin, okay? So, and these are not the only places where they are protesting, and this all has to do with what we are somehow also getting in touch, yeah? If you want to solve one issue with the energy crisis, then we have to look a little more broad. That is my suggestion. So, is it a good idea to grow biofuel then instead of food? Yeah, this is one of the questions which is present out there in the world. And one can study this quite nicely also about the palm oil imports and usage in the European Union, for an example. And so that is not food production. So this is in competition with food production, actually. The sad side is that in many of these countries where the palm oil is being produced for energy issues, actually the people have not sufficient palm oil for their own food, which is a very interesting development. Anyhow, so you see that actually almost 2/3 of the imported palm oil is being used for transportation or power applications. And I would like to cite one statement here. An increasing share of Europe's palm and soy oil imports is literally going up in smoke, and tropical forests are being trashed to meet the demands for supposedly green fuels. So that has been realized in the meantime by the European Union, and they are phasing out of palm oil for that reason, but they're doing it very slowly. So several of the negative impacts are going to continue, and so some people are actually not happy about that. So here you see that comparison. One more statement on this. The deforestation in the tropics for the cultivation of oil palms and soy releases vast amounts of carbon. According to a study recently commissioned by the EU, biofuel produced from palm oil has three times the carbon footprint of fossil diesel, 3 times more than fossil diesel, while burning soy diesel releases twice the carbon of fossil diesel. Biofuels are thus anything but green, so they have a negative, not negative, we have to be careful with the words, they are having a more negative impact, even from the point of view of CO2, okay? Energy-wise, anyway, it's not worth the discussion, probably. But yeah, and this causes actually conflicts around the world, which may matter also here and there. So, okay, let's go for our topic. Let's make a competition between solar and biofuel. Imagine you have 100 square meters of land, which you can either use for biofuel production, or you can use it for electricity generation by photovoltaic modules. So my question is, how far can you go with your car, which is either fuel or electric, with a yearly harvest from that 100 square meters? And so that's a comparison question. Do you think you can go 10 times more with the biofuel than with solar? Do you think it will be roughly about the same distance? Or do you think it will be 10 times more with the solar than biofuel? The best would be to make now question round, but we have to move on for time issues. But if you have some statement, I didn't get a clear suggestion. I will move on with my slide. You have to silence.
Zai, please put off your microphone.
Okay. So maybe I get some answers in the meantime. So that's
Zahir, please.
okay. So yes, we got some answers. Fantastic. So something between B and C. But here I'll show you the answer. In 2000 and somebody, can the moderator mute maybe some of the microphones? That would be great. So in 2013, the solar versus biofuel challenge didn't look good because you can go about 20 to 50 times more far with a solar powered electric car from the same grounds, 20 to 50 times. So it was very unfair of me not to even provide you or give you the chance to give the right answer. But it gets even worse for the biofuel because we go into the year 2021, and so I have a new slide on this one here. Where all this is based from actually is from the Fraunhofer ISE. I lost one of the references. It's about PV facts. So this was one 2013, and this one actually I have to edit from 2021. Now they increased the size of the grounds from 100 square meter to 1 hectare. That's okay. So we will increase the distance the car can go by also a factor 100. So this year the biodiesel can go 32,000 kilometers. So that's exactly the same number as before. But on the electric vehicles we got some improvements. And so we can now go 4.3 million kilometers. So that's 5 times to the moon and back, and you still have some spare. So the range difference is now increased beyond 100. So that's a pretty tough statement. So I hope it's getting clear that biofuel is not really the way to go when it comes to energy production and nature protection. Okay, so why did we get there at all? Yeah, somehow we wanted to talk about the combination of fuel production and solar energy electricity generation. So can we maybe solve 2 issues at the same time? With food production, we have the problem that it almost does not pay off. With biofuel production, we have all those destructive effects. So maybe we can have a good combination of these two. Can we have the best out of the 2 worlds? And so this brings us to the agrivoltaics, and I'm going to show just a few examples here, which are already existing in different parts of the world. So here you see, for example, a concept that is being developed together with the Fraunhofer ISE and growth of cotton crops and tomatoes at the Indian state of Maharashtra. Not so easy, sorry. So what is happening is that there is actually 30% less solar irradiation, so which has some advantages because it results in lower soil temperature in spring and summer and in higher soil moisture for the wheat crop. Here there is an example, sorry, there's one picture too much on it. Here's one example of the growth of berries. So the shading provided, the partial shading provided by the PV solar modules reduces the heat stress over the day. It reduces also the irrigation requirements, and the plants are not cooling so much out over the night. Yeah, we're talking about a moderate climate here. So and not all plants do want to stand in the full sun. So this is has been shown that it's very nice for the berries, but you can also grow banana and rice. And so the observations are, they're basically even better, that you have increased food production from those plants, but on the other hand, you save on the water. Yeah, so I would like to state that these benefits from agrivoltaics, of course, they may be not paying out for each and every plant, but already these examples are very nice. You can even grow edible fungi. They also do not need or do not want so much light. And the point is that with the electricity, you can use to apply the best possible conditions for the growth of these fungi. Yeah, and as it's stated on this slide here, 1 + 1 is not 2, it's more than 2. Yeah, so you have additional benefit when you combine these. There are also, let's say, estimations from the report from Oregon State University that if just less than 1% of agricultural land were converted to solar panels, it would be sufficient to fulfill global electricity demand. Yeah, and so 1% seems feasible. Yeah, if not all plants like to stay under the solar modules, 1% is a pretty possible number, I would say. Yes, this is the last project probably I'm presenting. This is on even you can grow wine under these conditions, and it has the same effects as stated before. There's a reduced water demand. You actually have a better growth of the plants during heat waves. And what these guys figured out is that there's an improved aromatic profile of grapes as an added value, yeah, for the wine growth. Okay, maybe this is the last example. You can even go with large large vehicles under certain installations if you do everything right. Okay, now why do we think that organic solar cells could be a perfect match for agrivoltaics? So what you see here on these pictures are polytunnels. So these are actually covering fully the regions of the plant growth. The sites could be open though, but specifically in moderate regions, this brings about an improved temperature profile. You see that here the plastic covers are also not 100% transparent, so they filter out some parts of the light. And our idea is that this could be quite easily replaced by organic solar cells. Let's have a look on the development of organic solar cells over the past few decades and the past few years. Over the past few decades, we see that there was little but consistent development starting from the 60s. And it took really off around the turn of the millennium. And we got specifically solution-possessed solar cells up to 11.5%. And actually, they stayed there for quite some time. But okay, in the vacuum, there were slightly better power conversions achieved. But then came the NFAs. What is that? This is the non-fullerene acceptors. So these are organic semiconductors, which are molecular in its shape, but they are not based on the fullerenes, which have been used basically for all of these efficiency records before. And with this new material class, the performances were pretty impressively rising over the last few years. So everything is moving closely towards 20%. What some people maybe never have expected it could ever happen. But this is the good news. So this has to do with the chemical structure of these materials and some more of these properties. But a part of this success is also due to the extension of the absorption spectrum more into the near infrared. So we can create much more current now in these organic solar cells because the absorption spectrum of these non-fullerene acceptors can be quite successfully modified. So what are traditionally targeted OPV applications? This is like building into integrated photovoltaics. And here the possibilities are very exciting because some of these projects have been realized where you can just place this into, for example, into some glass cover in some center, which may be empty now, but anyhow. And on the other hand, you can just glue photovoltaic modules to your wall. This is another possibility. That's reality right now. You can buy this and you can stick it on the outside of your house, so you don't need strong requirements. And you can imagine that the weight of these modules is a lot smaller. You can make these lightweight constructions here. You could use that the same way, just save on the construction cost maybe as the silicon modules. But we want to see quite another effect here. If you look on the right-hand side, you see here that in which part of the solar spectrum actually some vegetables are absorbing the light. Yeah, very healthy vegetables. And we see clearly that they absorb light mostly below 750 nanometer, and that there is a window of opportunity between 750 and 1300 nanometer. So roughly between 1 and 1.7 electron volt. So the question is, can we make exclusively near-infrared absorbing solar cells? Can we create those? And the answer is yes, with organic solar cells, and only with organic solar cells, because all other solar cells have semiconductors that do not provide a narrow band absorption, but a broadband absorption. They will therefore always cover also the spectrum that is required for the plant growth. This is just to show you another graph. This is where everybody is in agreement about where plants do absorb the light. Yeah, it goes up to the violet, ultraviolet, and extends out to the red, so almost the full visible spectrum. But beyond 700 nanometer, that is where we can use our window of opportunity. And what we did here is, so something shifted here. We did a little bit of calculation to estimate the power conversion efficiency potential. Yeah, so these calculations are basically looking into the question of what will be the power conversion efficiency, assuming only a radiative recombination. And everything is based on this Shockley-Quasar equation. And I would like to present you the results. Here we go from some low band gap up to 1.77 electron volt. Okay, that was the choice for our calculus here. Here you see the results. The open circuit voltage that we could expect from this calculation is, yeah, as we already know from the Shockley-Quasar limit on which this calculation is actually based upon, is somewhat lower than the band gap. So there is no surprise actually in that. But you see here that the short circuit current density, and that is a highly interesting thing, that yeah, you can get actually to quite some high short circuit photocurrents. As you see, we started around 0.8, 0.9 electron volt to consider it as the smallest band gap. But if you look at 1 electron volt, you see that there's like 25 milliamps per square centimeter feasible, even if absorption ceases at 1.77 electron volt. Yeah, and then you see here the calculated theoretical fill factor, and we get here to a maximum of 17% as a power conversion efficiency potential. Yeah, which most probably cannot be reached. However, a certain share of that clearly will be feasible, as it is already demonstrated today by the organic solar cells. So this is the bright perspective. Even if you only take 10% of this, we can still provide all of the sun's spectrum to the plants, for those plants who actually love it and like it, whereas we can keep the humidity at an improved level below this shading, or non-shading actually, below this OPV solar roof. So, yeah, these are actually the requirements. I think I should not repeat them one more time. We have seen this already. Of course, you need to have transparent electrodes, otherwise it does not really properly work out. Same is true for the charge transport layers. So we see quite some materials development ahead if these can be met. So, but how feasible is it? And are there any materials like that already out there? For that one, we show you just a few structures here. There are plenty of OPV materials already getting close to this requirement. Here you see most of these structures are these non-fullerene acceptors, but in the upper left, where you see those brackets, we have a few donor polymers of the newer generations. Yeah, and we also plotted the absorption curves, the normalized absorption, and that is what you see here on the right hand side. This is an overview of all the materials you have just seen one slide before. Here also, once again, for comparison, the chloroplast absorption. And we can already estimate that there's a very clear potential. I give two more examples. Here we have some of the donor polymers, and we see that some of them, for example, that orange one, appears to be very promising. And I also give you one example more for the acceptor materials. Here, as you see, it's even more easy to shift out the band gap to about below 1.5, maybe 1.4, 1.3, 1.2 electron volt. And to utilize that light, maybe specifically interesting is is that gray component, which not only extends most far into the near infrared, but also shows an absorption at where the plants actually do not take up most of the light. So this could be a nice possibility for synergy effects. So that brings me to my conclusions and summary. So worldwide, there are issues in food production. Farming often does not pay off. Instead, agriculture is done for creating biofuel, causing destruction of nature at several levels. Photovoltaics, on the other hand, is providing 100 times more yearly power harvest than biofuels. The combination of agriculture for food production and photovoltaics for power generation can solve both issues, given there are sufficiently low entry investments. And this is hopefully where specifically also organic photovoltaics can get into, if that technology is scalable, so that you can start off from small scale farming as well. So what we expect are improved revenues due to concurrent food and energy generation. So furthermore, general benefits of agrivoltaics are reduced irrigation and watering requirements. Agrivoltaics shows synergy effects for various plants, specifically in arid regions. Greenhouses and polytunnels can further improve the conditions for plant growth, specifically also in moderate climates to keep more heat. But the open environment is also possible for more arid regions. Uniquely organic solar cell-based agrivoltaic shows the prospect of full plant absorption spectrum utilization. Yeah, no other photovoltaic technology can do this. So I come to my conclusions. Given there will be a scalable OPV technology on the market, low entry-level investments can fertilize farmers to become local food and energy suppliers. This may be one important cornerstone to higher sustainability in agriculture and energy supply. Okay, so that brings me to the end. Thank you very much for your kind attention. I also would like to thank my group, which is showing up right here. And I make a last statement, not on my own accounts, but there's a conference taking place on agrivoltaics, and it's an online event in June, actually. And guess what? Today is the submission deadline for abstracts. So if you want to send an abstract in for that, you can Google it right now and go for that. So thank you very much for your attention.
Thank you very much, Professor Hoppe. Very interesting presentation. Sustainable approach for energy generation and also food production. Is there any question from colleagues? Yes. Just a small question, if it's possible, Professor Hoppe, about the storage of these photovoltaic energy. Is there any issue to adopt a sustainable approach also for the storage of these agri-photovoltaics?
Yeah, that is a very good question. The question is when and where you would like to utilize the energy. Do you need it over the daytime, or do you need it rather in the night? Yeah. So if you can, of course, make use of the energy in the daytime, it will be, of course, more easily to be economically viable or to realize that. If you need the storage usually adds up more than double of the costs, yeah, to the PV set. Yeah. So if you need storage, then you need to have good customers for the energy supply. Yeah. Mm-hmm.
Yes. Thank you very much again. And I propose to move to the last present talk in this session. Not the least one will be given by Professor Andrea Balducci on the key role of the electrolyte for the development of advanced electrochemical double-layer capacitors. Professor Balducci is Professor for Applied Electrochemistry and the Institute for Technical Chemistry and Environmental Chemistry and at the Center for Energy and Environmental Chemistry, Jena, of the Friedrich-Schiller University, Jena, Germany. He's working on the development and characterization of novel electrolytes and active inactive materials suitable for the realization of safe and high-performance supercapacitors, main metal-ion batteries, and polymeric batteries. Professor Balducci is co-author of more than 150 peer-reviewed articles, and I appreciate his talk, and it's honor for us, for me, to present him and to give him the opportunity also to present his work. Thank you.
Thank you very much, Sherif, for this kind of introduction. Good afternoon, everybody. It's a pleasure to be here. Everything is working fine, I suppose, right? You can see my screen, you can hear my voice. So I would like to change a little bit topic with respect to presentation, the very interesting presentation of Harald, which is actually, I think, sitting a few meters far from me. So we are not far away in the offices. And what I would like to talk with you is now not anymore about production, but storage of energy. So I think that we don't have to discuss too much about the importance of energy. Energy is one of the biggest challenges of our society for many reasons. The reasons that, for example, Harald was mentioning, but also related to the population increase, to the climate changes. And when we are considering this issue, of course, it's essential to work on the direction that was just mentioned by Harald, so generation. We need to find the sources like sun or other that are, of course, available and natural. But what is very, very important also is to store energy, because otherwise, without a very effective storage, all the effort in terms of conversion, production of energy would be somehow go lost, because in fact, we have a problem of storage. Like everything we like, we needed to be able to keep it for longer time. And what is very important to consider is that I think everybody of us knows that that is important to store a lot of energy. We wanted to have a very large amount of energy. But what is actually very important, to do, is that it's not just a matter of storage. So we don't have just to store an enormous amount of energy, but what is even more important is that we have to deliver this energy as we want. And this is an important point, because this is somehow related to the concept of energy on demand. What does it mean? It means that an effective delivery of energy is essential for the storage. And in our life, so in our daily life every day, we are facing many, many different types of situations. And each of them actually is requiring a specific energy demand in terms of amount of energy that we need to store and in terms of delivery time. And there are many situations in our daily life in which actually we want to have a very fast delivery of or uptake of energy. We are talking about minutes or seconds, so very short time frame. And we wanted to repeat this delivery of energy not just once, but we are talking about 1,000 or even million of times. This situation, so these, let's say, conditions that we are discussing are the conditions in which the so-called high power system are involved. So these are the generally defined high power applications. When we are talking about high power applications, it's probably helpful to consider a graph like the one that you're seeing in this presentation, which is that is actually a comparison of the energy and the power of energy storage devices. So here we have two of the most used energy storage system in our life. And we are talking about now the high power system. So we have in the blue side, the so-called supercapacitors or electrochemical capacitors, and in the red, the batteries. Now, batteries are known to all of you. Each of you are bringing a lithium-ion battery, either in a mobile or tablet or in the laptop. And these systems are very flexible in a sense, because these are systems based on a chemical storage. So there is a chemical reaction taking place while this lithium is actually moving from the two electrodes of the system. And these storage lead to the possibility to realize systems that have a very high energy. And in fact, lithium-ion battery are the batteries used on the cars, on the electric cars, that also Harald, for example, was mentioned before. But at the same time, you can also target them in a direction to make them as a power systems. That means systems that are able to deliver a lot of energy in very short time. So in this minute frame that we were talking before. Nevertheless, these systems have some limitations because if you wanted to go faster, so that means if you wanted to deliver the energy that they have in a shorter time frame, so a few minutes or even seconds, and as we mentioned before, these are cases that exist in our life, then they become very inefficient. And the fact that they become very inefficient make them not really the best choice for this. In this case, what is the choice for the device? And that is going to be a little bit the topic of my presentation, are supercapacitors. What are supercapacitors? Are systems that are relying not in a chemical process, storage process, but in a physical storage process. So what we are doing, actually, we are forming this electrochemical double layer. So we are polarizing an electrode, and then we are forming through a physical process a double layer on the first face of this electrode, which is not allowing large storage of energy, but what it can do is to give us an enormous power, a very high power. And because this process is much less detrimental than a chemical one, because there is no chemical reaction involved on this, or not significant, let's say, the strength of this technology is that you can use this system for 500,000, even 1 million of times, which is an enormous amount of cycles. The battery that you are talking about for cars are talking about 1,000 of cycles. An high-power lithium-ion battery, depending on the way you're charging, but we are talking about something like 10,000, 20,000 cycles. So what I would like to talk with you today is these supercapacitors. And when we are talking about these systems, we are talking about system, so with high power, very high power, very long cycle life, and they're also called electrochemical double layer capacitors. So this acronym here, EDLC, stand for this system, are synonym in a sense. Now, these systems are available, so you can buy them. If you would Google, like you can buy a lithium-ion battery, you can also buy supercapacitors. They have a very similar shape. So in this case, for example, you are seeing what is called a cylindrical system, because it's like a typical battery that we are putting in our remote control, for example. Or you can have a battery which is called a prismatic, which is more similar to the one that one can have in the mobile. How they are working this system? Basically, they are consisting in a sandwich of two electrodes that are typically made of carbon, coated in an aluminum current collector, divided by a separator, which is paper, in which then you are wetting, or you are basically impregnating an electrolyte, which is made on an organic solvent, in most of the cases acetonitrile, in which you are dissolving a salt, an ammonium salt with this BF4 as an ion. I don't want to go too much in detail, but what is important to know for the moment is that the cell voltage of this system nowadays, of this commercial system, is in the order of 2.83 volt. Now, what you are seeing here is an indication that probably many people are not so familiar with. So, you know, we know very well how big and important will be the market of the lithium-ion batteries, but electrochemical capacitors, so the electrochemical double layer capacitors, is also a market. So they are an industrial reality, smaller than the lithium-ion battery, but which has been constantly increasing over the year. And what you're seeing here is an estimation, which is rather conservative. There are estimations that are even more, let's say, favorable for this technology. And what has been estimated is in 2022, so next year, we will talk about a market of 1.5 billion of euro. So not an enormous market, but let's say not a small one, which is then definitely increasing over the time. And this market is divided in two main sectors. One are the small supercap. These are used for electronics, for example, the flash of your mobile. And then there are the large scale electrochemical double layer capacitor, we are talking about farad, so this F here stands for farad, so more than 100 farad. These are used in electrical engineering. And what you can see in this graph is that these systems will be more and more used in the automotive sectors, so buses, automotive, and this will be actually the bigger share, the larger share of this market in the future. Now, present application of this system. Probably some of you have a supercap in his hand. For example, in the flash of the mobile phone, you may use a supercap. But they are very much used also, for example, in port crane, with a photovoltaic on wind, for example, to buffer fluctuation because they're very fast. In the automotive, to, let's say, optimize as much as possible the consumption of the fuel. In some car manufacturers are already introducing the supercap in the start and stop applications. You know, when you go to the traffic light, your car is switched off and then on. To switch on, you need a lot of energy in short time, and you do that for many times. This is a classical application of supercapacitor. There are also in aerospace, or a very nice application in buses. So buses are powered by this system because basically what you do is that you can think about that you can power a bus just with these devices, because typically you don't make a very long distance between one station to the other. And then in the time in which the people are going out, in, you can charge fully this system. So you would have them enough energy to go to the next station. The energy density, to give you some numbers, of this device is in the order of 5 to 8 watt-hour per kilo. When we are talking about battery, we are more than 200 watt-hour per kilo. This is the reason why, if you wanted to buy energy from these systems, you don't make a good deal, because it costs 4,500 euro per kilowatt hour, which is order of magnitude higher than a battery. But what is very convenient is to buy power for this system. The cost for a kilowatt of power in this supercapacitor is less than €1. And in battery now we are talking about almost 100 or something. So it's exactly complementary than a lithium-ion battery. These are properties that make this system very, very appealing for the application that I was mentioning to you right now. But in the future, so in this automotive application that I was mentioning to you, what is the challenge that this technology needs to face is to increase the energy density and to reach values that are in the order of 50 to 20 watt-hour per kilogram, and to reduce the cost in the order of 3,000 or less than 3,000 euro per kilowatt-hour. Why? Because basically what we need to do is to increase the energy of this device to introduce them in electric car or in buses in a massive way. Because basically then we would have a system which is able to deliver the energy that this system are needing for specific application like start and stop or power other part in very short time. And doing so, they would make more efficient the use of the battery and prolong the life of the battery. So one of the big challenges on this system is really to increase the energy density and to reduce the cost of the energy in the future. Now, what is interesting to notice, this is more from the engineering point of view, but I guess this is an information that is also nice probably to think about, is that nowadays the cost of the components of this cell is divided basically in almost 1/4 for electrolyte, electrode, the separator, even if it's paper, because there is a lot, it costs quite a lot, so 23%, and then the cell part and the production of this system account for 22%. What has been estimated that only by engineering, so only by optimization of process, the cost of the separator and the cell part and production can be reduced significantly in the future. What then will be the consequence of this reduction will be that the share of the material and of the electrolyte of these devices will become much, much larger. So we're talking about 38 to 37%. And from the Bastian point of view, what is very important to reach is a target of a cost lower than 20 euro per kilo. So that means in the future, electrolyte and electrode components should all cost less than 20 euro per kilo. Otherwise, it will become a little bit like the question of the milk that Harald was mentioning. They are producing, but they will never get money, and they will not do this, because this is not a primary need. What you can do to reach this goal is actually to work in several directions. So the electrode, the electrolyte. These are a kind of technical slide. I don't want to go much in detail, but what I want to say is that if you wanted to make an improvement of this system, you cannot just improve the material, but you also have to improve the electrolyte. And what I would like to explain to you now in the following presentation is why it's so important also to consider the electrolyte. It's important because in these systems, whereas I said before, basically you are storing energy at the interface between the electrode and the electrolyte is an active material. So even if there are not an electrochemical chemical reaction taking place, what you need is to bring the ions of this electrolyte, so basically the positive and the negative charge of the salt that you are dissolving in acetonitrile, close to the electrode. And actually this electrolyte need to display a large number of properties. For example, needed to display a large electrochemical stability, because the higher is the potential, we will see in a minute, the higher is the energy. And what we learn is that we wanted to increase the energy. We should have a low melting and high boiling point, because basically what we want to do is to use these devices in a very broad temperature range. So for minus 40 degrees, typical application, very cold north country in the world, but also very high temperature. And here, what we have to consider is that we are talking about also temperature that sometimes may reach 80 degrees C. What we want to have a very thermal and good chemical stability, they have to be cheap and they don't have to be flammable. So actually we want to have a lot of information, a lot of properties out of this system. And the electrolyte of nowadays, they are working pretty well actually. They are very good because they have a very good conductivity. You can use them very well at low temperature. The cost is not too high, but they have a problem. The problem is that you cannot go higher than 2.83 volt. And this represents a limitation, because if you wanted to increase this energy to 15, 20, as we said before, you cannot do this. Because basically, as you can see in this formula, you needed to increase substantially the voltage to increase substantially the energy. And so there is a lot of work on the use or on the introduction of alternative electrolyte for these systems. And now, I don't want to go in detail on this part. In this case, you have to believe me a little bit. Let's say you can categorize this an alternative that has been proposed in the past in many categories. Let's say one is the use of alternative solvents. So that means instead of using acetonitrile, we use another solvent, another organic solvent. Water is a very good solvent, but it has a problem. The electrochemical stability of water is very limited compared to organic solvent. That means you cannot realize high voltage system. Water-based systems are working in the range of 1.2 volt. Here we want to go up to 3.5 volt. You can then try to exchange the salt. So instead of using the salt that I was mentioning before, you can use an alternative one, trying to make it larger in terms of electrochemical stability. Or what you can also do is to get rid of the solvent and to use molten salt, so liquid salt that are liquid at room temperature. These are called ionic liquid, which could, in theory, be very, very beneficial, because then you don't need to do anything else than to put this salt inside. As I said, there have been a lot of work on this, and actually what has been found out, you can see here, is that when you are considering the operative voltage that is accessible utilizing this alternative electrolyte, actually you can improve the operative voltage of the system. But then one has to be careful, because when we are talking about this high power system, what is especially important for us is to increase the energy of this system, but in well-defined condition. What are these conditions? When we are applying high current. Why? Because the application of high current implies short time. So we don't want, as we said before, to charge this system in 1 hour. It doesn't make any sense. It has a low energy, it's costed too much. We will use a lithium-ion battery. We wanted to charge this system in a minute or second. And if we do so, we need to apply high current. And what we realize actually that if you apply high current, at the end, the performance in terms of energy and power of the systems containing alternative electrolyte are not better than the state of the art. And this is the consequence, this is the reason, sorry, why nowadays there are not alternative in commercial system. There are a lot of studies on this, but still the system that you can buy are containing this conventional electrolyte that I was mentioning to you before. And so this is certainly a point of importance for those people like me that are working on this field, because it's a message which is quite clear. We need to do better. We need to do more. And so what I would like to show you in the last 5 minutes of this presentation is actually how you can try to do this work, how you can try to go in the direction of eventually improve the electrolyte of this system. And what you see here is basically that if you want to do so, you need to consider 3 main pillars. One are the identification, so to try to identify new components. One is the characterization of this component. And one very important is the interaction between this novel electrolyte and electrode. And because basically what you need to do is to optimize as much as possible this interface to improve the life, to improve the energy, and so on. Now, what is desirable is to try to rationalize as much as possible the search of new material. Because, of course, as a chemist, for example, I'm a chemist, as I think also many other people here in the audience, what we can use is to use our knowledge of physics to try to identify alternatives. But actually, this process is very time-consuming. So what we were trying to do, and this is, I would say nowadays, a trend in the energy storage community, is to apply computational screening approach to identify new component. What does it mean? This means that we were trying to build up, or you can build up, an interface between electrochemistry, so I'm an electrochemist, with people working in computational chemistry, because basically what you want to do is to generate a loop. So you, as an electrochemist, you are basically supplying your desired properties. And then the computational chemistry is able to set up a screening of existing compound, out of which you can get candidates, which then will be validated. Now, this seems to be a kind of abstract approach, but I can tell you that it's not. There are a lot of also industrial interest on this. Why? Because basically what you can do is to handle extremely large number of compounds, for example, 67 million of different compounds, which have been produced. You know, there are an enormous amount of chemical compounds that are available. Some of them are commercially available. Some of them are available on demand. Some of them are being synthesized. But there is a kind of database which is accessible where all these compounds are there. And then basically what you can do is, to this computational screening, to realize a screening. So a hierarchical down selection strategies, well, basically you set up target and you say everything is, for example, including this target is in, everything not is out. And then, sorry, if you do so, you can end up to something like 1 million of polar organic liquid. And then you can do a step forward. You can make a refined selection that you basically do on the basis of the input of the electrochemistry. And if you do so, then you have to take a decision. The decision is either you're looking for everything has been synthesized on this database and will be thousands of several thousand of compounds, or what you can try to do is to spot commercial systems. So that means a system that have been commercialized, that are available, you can buy, but that were not used before for this specific application. For example, this trichanopropionic acid methyl ester, this is CPAB. And what I wanted just to show you is that doing so, you identify basically systems that have, for example, viscosity which are higher than the state of the art, but still reasonable for a use in application, with a higher boiling point and a higher flash point. That means properties that are going on the direction of the safety of this system. And then what you can do is you can use this system in devices. And for example, what you can see is that you can charge and discharge. So that means you can utilize a system at 3.5 volts. So the state of the art at 3.3 volt. And what you're seeing here on the right is a so-called float test. Just a few words about this because probably it's interesting for you. A float test is an industrial test. In this test, what you do is that you are holding the potential of your system at a certain value. For example, 3.2 volt. And then the industrial target is that a device, in order to be commercialized, need to be able to retain 80% of its initial capacity after 500 hours of float time. And as you see in this case, for example, in a lab scale, we were almost basically reaching this target. And then just as a slide, a conclusive slide, if you then started to play with the combination of salt and solvent, you can, in fact, realize a system with very, very high stability. For example, you can realize system working at 3 volts or even higher, which display extraordinary retention. For example, retention that would correspond to something like 5 million of cycle, which is something possible because basically you don't do any chemical reaction, but you are holding, you are making a very stable system based on this physical process. And so, as a conclusion, I hope that I was not too long. What I hope I was, let's say, showing to you was that these ADLC are actually an industrial reality. They are used and they have a market which is increasing. When you are considering this system, the electrolyte is a very important component. We need a novel, cheap, and non-toxic electrolyte, and what we need also are new ideas to develop this electrolyte. For example, this screening process I was mentioning, but there are also many others, because actually this will be one of the key to develop devices that we can introduce in our daily life, and they can help us to realize a better storage process, which is actually what we wanted to do to solve this energy issue that we were discussing at the beginning of the presentation. And with that, I'm at the end of my talk. I would like to thank you, the DFG and the BMDE for the financial support. All my co-workers. There are many people. That's why I was not mentioned, because there are many people working on the ER here. And I'm happy to answer your question if you have any. Thank you.
Thank you very much, Professor Balducci. I think that Dr. Ashraf Shbid requested for a question. Yes, Ashraf.
Thank you very much, Professor, for this presentation. I have a technical question. As we know, the specific capacitance can be measured using 3 methods: from agrivoltaimetry, from galvanostatic charge discharge at a specific current excitation, and from impedance spectroscopy. So my question is, what is the suitable and the best method that can give rise the real result? So why we don't found the same capacitance value when using those techniques for the same device?
This is a very good question. So we are going to the base of electrochemistry. So let's say you don't get exactly the same value because you are approaching a system utilize different conditions. So a good practice is to calculate in a lab scale the capacitance of a device utilizing the 3 techniques that you were mentioning. So CQ voltammetry, galvanostatic charge discharge, and impedance. One has to be careful anyway, because depending on the material, if you're using a carbon, so this electrochemical double layer, the CQ voltammetry is a very straightforward technique. But if you're using other material, so-called pseudo-capacitors, it can be a little bit more complicated, because actually you're having then chemical reaction taking place. So one has to be careful. Regarding your question, is depend on the direction in which you want to go. Industries are utilizing impedance and galvanostatic charge discharge. They don't do CQ voltammetry. But in the lab scale, it will be very important to use all of them, because each technique is supplying different information, which are very, very important to develop than your material.
Thank you very much, Professor.
Sharif, sorry, but I didn't understand your question. I was very, very far.
Sorry. It's okay.
No, it's better.
My question is about applications very interesting for Africa, such as health vagoon and also agricultural use of these storage energy storage systems.
Definitely. I mean, we were trying, no, also to do something in this direction together, also with Wasim. I think that they could have a presence because these systems are not especially large, so you could even include them in already existing systems, train or let's say foil of different nature can be implemented. And that could be definitely an interesting application. Also because, for example, thinking about the temperature, they may have the ability to work at high temperature. They are, let's say, intrinsically more safer than a lithium-ion battery. So if you are working at 60 degrees with a lithium-ion battery or a supercap are much more safer. So in this context, they could have, let's say, they could be of interest as a device for storage to be implemented with different type of system, of course.
Okay, thank you again. Okay, yes, Ashraf.
Harald has a question, I think.
Your mic, Ashraf.
Harald, your mic is muted. Can you?
Okay, thank you. Okay. For the case of cycling retention, sometimes we found in the literature a value of 110 or 120% after 3,000 or 5,000 cycles. We can explain this phenomenon.
This is actually something that is not unusual. So to have a lab systems that is cycling 100,000 of time is possible because the efficiency of the charge and discharge is very high. So, you know, basically, when you are charging this system, if you are not exceeding the condition, it's not a big deal to go to 100,000 cycles. So this is actually related to the intrinsic physical process that was mentioned before. So this is not a problem. Flow to test are more challenging. Then here we are talking about 500 hours, but there are if you have a good electrode and a good setup, these are values that are reachable with a conventional material. So it's not a deal, even in a lab scale.
Thank you very much, Professor.
Yes, thank you. Is there any question, please?
Yes, here.
Yes, Professor Harald.
A short one. Thank you very much for the very interesting presentation. So I have a question concerning the application of the supercapacitors. I mean, it always seems to be connected to some movements or something. I mean, like in transportation, you need a really high power to compensate for some of this. Do you see also other applications or possible applications where this high power could make specifically a change?
Yeah, stationary. So windmill. For example, one of the big problems of the windmill is that sometimes they are subjected to very fast changes, right? Maybe you can have a strong wind and then stop, or you can have let's say a situation in which you don't have wind and then the wind comes, start to blow. In this case, the high power system are very important because they can buffer this strong variation, strong variation in short time. Actually, there are already in many windmill the supercapacitor integrated on the back, because basically what you can do is that you can use them to exactly buffer this system. Also for the grid, again, so more larger scale, not only on the let's say first step, but also on the grid, because then you could stabilize. This is also one of the point, together with a big battery, the grid when you have big fluctuations. So a little bit what you were mentioning before, right? That you needed to buffer because you may not have a constant input. And these are actually I've been seeing that they are actually quite helpful in this, together with batteries.
Okay. Thank you.
Yes, thank you. Is there any question from colleagues? Thank you again, Professor Balducci.
Thank you. Thanks for the invitation. Have a nice weekend to all of you. Bye-bye.
Bye.
So, Professor Balducci, thank you very much, okay, for that you accepted our invitation and you gave this very interesting talk. And I hope you are already cooperating with Professor Sherif. Are you in cooperation already, or do you have any cooperation with Africa?
We were actually submitting a proposal. I have a friend, Wassim, which I was working in France, and we were having, this is the French Connection Super Cup, and with Sherif, we were trying to write a proposal. We wrote actually a proposal together. It has been not, let's say, funded, unfortunately, but we were definitely interested to continue also in the future. And I wish we will have this chance soon to initiate also a active collaboration with some African partners.
Yeah, because I think in Africa, this storage issue is very important, and not much is done in the field of storage in Africa. A lot is been done in other type of, generally on photovoltaic energy production, but energy storage there's very little done. I think this is an aspect where knowledge transfer should be promoted. Yeah, knowledge transfer from Europe to Africa, and I hope Professor Balducci, we can integrate our network. That's why this network, ANSOLE network, is there to bring scientists within Africa and outside Africa and Latin America to work together and exchange ideas and advance science, and especially to educate and help young scientists in Africa acquire knowledge and build capacity. So we'll be very happy if you open your lab like Harald Hoppe has been doing. So a lot of African students have gone through his lab and finished their, and there's still good numbers there now coming from Nigeria and Cameroon, and so doing their PhD with him. But I say in the field of energy storage, it will be something great. So if you can get some students, if you need students, we'll provide you students. But as you said, one need funding to really go into good cooperation with Africa. And I think there are going to be some call, EU-Africa calls funded by the European Union. The last Horizon 2020 call, which where the submission was on the 26th of January, just passed. But I know that there are calls coming the next few months where Africa will play, cooperation with Africa will play a big role, and energy will play a role. So I think, I hope that your group will submit a proposal with already the Professor Sherif or other groups in Africa. So think about Africa. Think how we've been discussing today before you came about relationship between Europe and Africa, and we said the relationship should be at eye level. The big issue with Africa so far is that there is lack of funding, research funding, and in many African laboratories. But you have highly motivated researchers, students who like to achieve high goals, but they are limited with due to lack of funding or lack of equipment in their laboratories. So this cooperation, Africa-Europe is there to remediate this problem. So I will be happy for you to join our network. Membership form, I can send it to you, and then it's a good thing. You will not regret it.
I'm sure. Thank you. I will be happy to to exchange with you. Okay.
Thank you very much for accepting our invitation. And we are just here. I've never met you personally, but the next I think the next Christoph Ulbrich knows you from Münster. I think that's what you told me.
Yeah, exactly. I read the name of Christoph. Yeah, we were working, both of us. It's a small world, actually.
Yeah. So he was there.
Yeah.
Christoph, are you around? I don't know. Christoph?
Oh, yes. Hello.
Yeah. Christoph, you told me that you know Professor Balducci while we were in Münster. So, okay, he's now in Jena. And Harald is my friend for many years. We've done a lot of work together. I can say the majority of my papers this last years were together with Harald. So the world is a small world, so people meet. So I think, and Christoph, maybe when you have time, you can pay a visit to Professor Balducci the next time you come to Jena. He's in Linz, but I think he's looking for something also to work on. Yeah. So thank you very much, Prof. And we'll keep in touch. I will send you the membership form. So Harald and most of his team are part of this nice network, and we think that this storage aspect is very, very important for Africa. So a lot is done for just energy production, but energy storage there is more to do in Africa. So if your expertise your knowledge can be transferred, that would be wonderful. So thank you very much.
Thank you again for the invitation. So have a nice conference. Bye-bye.
Yeah, bye.
Bye.
So I think we have a short, what's the time? I've just taken the break. That was the break time, but Christoph, you can prepare yourself for the moderation of the next session. Professor Sherif, thank you very much.
Yeah, you're welcome. Thank you. I'm waiting your answers.
Yeah, so you see, I'm trying to work for us, for Africa, and thank you that you are in the organizing committee, and you are the one who brought in Professor Balducci so thank you very much. Thank you.
You're welcome.
So I thank all those who presented in this session, Harald and Moufid, and Shahidul, and also Professor Balducci. Thank you for your nice talks. And the good thing is that people can watch the talks even after everything is recorded and it's going on live in YouTube. So it's a good event. Thank you very much. Okay. Christoph, so you take over.
So we'll have a break. We just continue.
Just continue. Let's continue. Let's get time because there's no need. My talking was a break.
So the next contribution on desalination, energetic aspects, and coupling with solar energy will be provided by Professor Sadok BEN JABRALLAH. Professor Jabrallah teaches at the University of Carthage. He is a co-founder of the Laboratory of Energetics and Thermal and Mass Transfers. His research team, Transfers, Flow, and Phase Change, works on thermal, fast change, solar desalination. Moreover, he coordinated several projects in the field of desalination, including a federated national project to study the feasibility of solar desalination in Tunisia, and he launched and coordinated master degrees in air conditioning. Professor Jabrallah, the floor is yours.
Yes, hello. Can I share my screen, please? Can I share my?
I guess so. You have to.
Yeah, it's getting, yeah. Mm-hmm.
Please, do you hear me?
Yeah, we hear you. We hear you.
Yeah, yes. Do you see my screen?
Yes, but now it's switched back.
You switch back, so you have to go back to your screen. Share the screen again.
Okay. Do you see my screen, please?
Yes.
Yeah, we see. Yeah, we see.
Okay. I can begin?
Yeah, I can begin. You can make it large if you want. Presentation, yeah, there. Click.
Like this?
Yeah.
Okay. Okay. Thank you so much for the invitation, and it's a great pleasure to share with you these few ideas of subject that links energy and water. Like energy, water is the focus of many government, and the lack of fresh water is a big problem that needs to be addressed. Water is necessary for life on Earth. I will talk about the energetic aspect of desalination process and coupling with solar energy. In my presentation, I will introduce the subject, and then I will talk about desalination process, both thermal processes and membrane processes, and I will talk about solar energy and conclusion. Okay, the water amount in the world is about 1.5 billion of cubic kilometer, but 97% is in ocean and the seas, 2% in ice, and only 1% on soft water. With economic development and population growth, available fresh water is not longer sufficient for the world population. Add to that unfair distribution of water. In this map, we see red zone, the country will suffer from deficiency of water, and orange zone with country which local resources are not enough to needs. We see that African continent is a lot of work to do in the subject of water. Desalination of sea or brackish water can help solve this this problem. The desalination is it new? Is not new. It is very old. When we came back in the history, we see Aristotle gave two ideas. The first idea is seawater is made drinkable by evaporation. Wine and liquids can be submitted to the same process. After reduction as humid vapor, they again return as liquid. This is lead to one category of process is thermal process. The second idea of Aristotle is when a clay vase, well closed on side, is introduced in sea water, it can note that the water that penetrate through the pore is drinkable, and this is the second the second idea. It leads the second category of desalination process called membrane distillation, because here we use membrane. The desalination was used in history and was described in books. The first was Jabir ibn Hayyan. And the first desalination plant in Earth now, in history, was built in Tunisia island, called Jerba, by a group of Spanish soldiers surrounded by the Turks to produce 40 barrels of water per day. As we saw before, the desalination process, or as said by Aristotle, the desalination process can be divided in two groups, in two categories: thermal process and membrane process. In thermal process, desalination and freezing. And membrane process, there is reverse osmosis, electrolyze, and membrane distillation. I put this in color because membrane distillation, there is distillation and there is membrane. This is a new technology of the desalination. In distillation, there is single stage, multi-effect distillation, multi-stage flash distillation, and vapor compression. Single flash distillation is there is two step. The first is evaporation by heating water, and the second is compression. Is condensed vapor obtained. Evaporation needs energy, while condensation provides energy. Energy consumption by distillation have two parts: energy consumption by water heating and energy consumption by phase change. Here is evaporation. All the energy is thermal energy. Multi-stage flash distillation process is based on evaporation, flash evaporation phenomenon. So we have to make vacuum, so we need pumps and heating the water. Multi-effect distillation based on reuse energy provided by condensate in the next stage. So we have pump. We need pumps for reduction the pressure and heat and energy, thermal energy for heating. Vapor compression distillation. This is we have to produce in vapor and then condensate it, but in this case with the mechanical system. Energy consumption by all these processes, MSF, multi-stage flash, and multi-effect distillation and vacuum compression have different parts: heat, energy for heating, energy for evaporation, and energy for pumps. There we need both thermal and electric energy. Membrane distillation is a relatively new process based on using of hydrophobical membrane that allow vapor to go through but not liquid. So we have separate vapor from liquid, and there is 4 configuration dependent on the system of condensation of vapor. This processes is now the subject of research in laboratory. Energy consumption by membrane distillation, there is 3 parts. Energy consumption by heating, by water heating, energy consumption by hot water feed pump for evaporation, and another one, energy consumption by cold water feed pumper for condensation. We need also thermal and electric energy for pumps. Freezing is not used very often, but energy consumption by freezing have 2 parts, one for cooling and the second for solidification. So we have need the thermal energy membrane process, reverse osmosis and electrolyze processes. Reverse osmosis is based on use of semi-permeable membrane. When this membrane separe brine and water flows from low concentration of salt to high concentration. There is a pressure difference called in this case osmotic pressure. If we want to reverse this flow by applying in this case by applying pressure greater than osmotic pressure, flow water is reversed and water flows from higher concentration solution to lower. So we obtain fresh water. The only energy need here is electric consumed by the pump with high pressure. I observe here that the pressure here are very high, more than 30 and 40 bars. We need only electric energy. Electrodialysis is based on apply of electric volt difference, and the ions will be attracted by electrode, and we obtain the clean water. So for electric dialysis desalination process, the energy consumption per volume is given by this expression. Only energy electric. So let's have a look on energy consumption of main desalination process. This table shows that reverse osmosis has a low consumption, energy consumption, and but MSF, multi-stage flash, and multi-effect distillation has the relatively high energy consumption. This has an impact on cost of water and production. So we can observe here that reverse osmosis in both seawater and brackish water have a low cost for a cubic cubic meter of fresh water. This is explains why the reverse osmosis is used in majority in the world. We have to respond to this question in this presentation. Is the solar desalination possible? It is convenient or no? Of course, solar desalination is possible by two-way, direct solar desalination or indirect solar desalination. And for the direct solar desalination, we see there is solar steel humidification, dehumidification. Solar steel, example for solar steel, there is many types of solar, many configuration. Humidification, dehumidification, where evaporation is separated by evaporation and condensation, where are separated. Indirect solar desalination, we have here to produce electricity, electric energy, and thermal energy, and combine the two types of energy to desalination. So we use photovoltaic panels or and solar collector and solar pound. Energy and for thermal energy or electric energy also. So this is an example with multi-stage flash coupling with solar energy. We need electricity from solar collector or solar pound or power grid, and thermal energy. Membrane distillation coupling with solar energy. This is an example. We need electricity for pump and the thermal energy for heating, so we can use power grid or PV and solar collector, solar pound. Reverse osmosis coupling with solar energy. In this case, we have only need electricity, so we can produce it from solar collector or solar pound, and to supply the process or the installation, the system of osmosis reverse. Electrodialysis coupling with the solar energy is provided by PV for electricity. Here we need only electricity, so we have PV for electricity and supply the system. Concerning the production and cost water for solar desalination, we can show in this table that there is some solar desalination process who have a low cost, the low cost per cubic meter of fresh water, but some of them membrane distillation, reverse osmosis. When we try to use solar energy for this process, the cost is relatively high. We have to, in conclusion, we can say, desalination continued to grow to the increased water scarcity in many parts of the world. The increase in population, industrial, and economic, all desalination processes have a very high energy consumption, and although the current water production cost from solar energy coupled desalination systems is much higher than the water cost of conventional desalination systems. However, this high cost is offset by the energy benefits. Due to this high cost, desalination system incorporating solar energy resource are currently only economic in rural area without access to electric grid, where water scarcity is a major problem and where solar radiation is appropriate. I have a personal reflection or idea. When water becomes scarce, the cost, even if it is high, does not prevent the adoption of desalination. Thank you very much for your attention.
Thank you, Professor Jabrallah. Are there any questions? Okay. If not, I want to thank you again, and we will continue with the next speaker. The next contribution is from Hadu El-Ghazi on doping and indium optimization of PN indium gallium nitride solar cell performance and analysis. Hadu El-Ghazi is affiliated with Renewable Energy Group of the ENSAM laboratory of the University of Hassan II, Casablanca, Morocco. Yes. Mr. Ghazi, we are looking forward for your presentation. Hello? We are looking for the next presenter. I know we are a little bit early, but I was thinking we just continue, but.
No, I thought I saw him come. He was in the waiting, but normally you ought to come on time.
No, we are a little bit early. The thing is, we finished the previous one a little bit before time, but yeah, I mean, we do now a short break for, I think it would be 6 minutes.
Is the next person, the next speaker, Elyes Bel Hadj Jrad of University of Sousse already there? Is it there?
I don't know.
Yeah, he's here. He said, yes, I'm here. So can you speak? Yeah.
Okay.
So can you present? Can you, Harald, can you allow him to share his screen?
Okay, it seems to work. So then the next presentation, for now we skip.
Hello?
Hello.
Do you hear me?
Yes. I think because it's a rather short time, I would say the title is here and you're here. The floor is yours.
No problem, but I'm sharing my screen. Do you see my screen?
Yeah, we see your screen. We see your screen.
Yeah.
Okay. So I want to thank you, first of all, for the opportunity you offered for us. I'm very glad to be present here today. and I'm glad to present for you our work entitled Development of New Numerical Platform for Photoelectrical Parameter Extraction of Hybrid Nanocomposite-Based Solar Cells. So my plan is divided as follows. First of all, a brief introduction. Then we will discuss the methodology, our adopted strategy, some and finally, we will finish by some conclusions and outlooks. So as we all know, the main strategy to produce energy is by fossil energies, such as natural gas, petroleum and coal, which are very exhausting and expensive in terms of consumption and exploitation. That's why the recent research focused on the renewable energy, the hydraulic energy, the biomass, the wind power energy, and in particular the photovoltaic energy, which will be our the interest of this work. So why hybrid solar cell device? First of all, I want to classify solar cells as follow. There is inorganic solar cells which provide good efficiency, but unfortunately require expensive manufacturing techniques. There is also organic solar cells which provide high flexibility and low cost aspect, but sometimes involve some toxic materials and provide low efficiency. And to compensate these issues, there is hybrid solar cells, which are in fact composed of organic and inorganic materials. The organic matrix offer the low cost aspect and provide more flexibility, and there is the inorganic materials which enhance absorption and improve charge transport characteristic. So what is hybrid solar cell issues? First of all, a complexity of many physical and photoelectric phenomena, and poor photostability of organic materials, an unstable response under different physical conditions, I mean temperature and pressure, and also low efficiency in relation to manufacturing costs. So the objective of the study that we will initialize a numerical platform for solar cell parameter extraction. Next, we will choose the appropriate method for parameter extraction, and we will apply the method using MATLAB software and simulation of the results. So the numerical platform is based on the EDV characteristic of the solar cell under illumination to provide electrical parameters such as series resistance, shunt resistance, ideality factor N, saturation current, and photocurrent. In fact, the numerical platform is based on 3 different approaches: the physical approach, the mathematical approach, and the numerical approach. And of course, it should be compatible with simulation softwares. So in fact, there is several ways to extract the parameter from solar cell. There is evolutionary methods, iterative methods, and analytical methods. And in this study, we will focus on, or we will use iterative methods and analytical methods. So the physical approach is based on the single diode model, or the single diode equivalent circuit, which provide for us the Shockley model as follow. And as we can see, this is a nonlinear equation which contain the 5 parameters which we aim to extract. So then a mathematical approach is applied. It is based on the Lampert W function, and the Lampert W function will transform the implicit form of the equation into an explicit form. And I mean by implicit form, a form which is difficult to manipulate. The numerical approach will then be used using Nildermith algorithm, and it has as input the Lampert W function to provide for us a vector X which contain the 5 parameters which we aim to extract. And in fact here, to ensure that we have well optimized parameters, we will use the root mean square error function as optimization criteria under imposed tolerance. So in the adopted strategy here, I want to show you the evolution of our work since 2008. So this platform was first of all used on a nanocomposite based on polyvinyl carbazole and nanocrystals of titanium dioxide based solar cells. And the method has proven that we have for this structure low photocurrent densities in nanoampere order, charge transfer limitation due to the matrix polymer, and a high space charge formation. And for that, we thought about the performance enhancement by trying many polymer matrix. So as we can see from the curves here, the polyethylene, also known as P3HT, provide a considerable increase in the current density. And this is due to its regular morphology, its high mobility of charge carriers, which lead to a mobility increase, a low conductance, and a fill factor increase. We also think about changing the inorganic material, and we have found that silicon nanowires provide for us the better performance in this study. So as enhancement, we can see here that the density of photocurrent is bigger 100 times magnitude of the recent structure. So in fact, we have applied the method on the same structure, I mean P3HT silicon nanowires based solar cells, to check the other electrical parameter of the solar cell in order to understand, to better understand the mechanism of the charge transport. And I want to mention here that we have observed a large error in the negative gap of voltage. As we can see here, there is not a good fitting, or there is a bad fitting between the experimental curve and the theoretical curve. And this high error rates can cause inaccuracy in terms of the electrical extracted parameters. So in order to enhance the numerical approach, we have imposed two extra conditions. A tolerance was imposed to control the step between two consecutive iterations, and a second tolerance was used to impose calculation limits on the calculated current. So then the improved method was applied on the polyethylene silicon nanowires based solar cells, but this time before and after undergoing some chemical treatment on the surface. And as we can see here, the structure without treatment present a very high series resistance, and a big ideality factor, which is bigger than 2, and low photocurrent. And I want to show you here that we have well improved the fitting in the negative gap, which is very important and can lead us to more accurate results. Error here, the error was 10 order minus 2 and become 10 order minus 4. So as the first treatment, the surface was treated with fluorhydric acid, and we have well optimized the series resistance, the saturation current, and the photocurrent, but the problem remained for the ideality factor, which remain bigger than 2. So we thought about a second chemical treatment. The surface was then grafted with polystyrene-derived molecules, and from the table here, we can see that we have well improved the series resistance, the ideality factor from 2 to 1, the saturation current, and a considerable increase in the photocurrent. So as conclusion, the digital platform has shown a good fitting with root mean square error from 10 minus 2 to 10 minus 4. The chemical treatments improve the electrical parameters of the able structure P3HT silicon nanowires, which lead to a performance enhancement. And we aim to modify the algorithm to ensure convergence even if the initial solution is poorly chosen, and to enhance the structural performance by application of extra chemical treatments on the surface. Thank you.
Thank you for your presentation. Are there any questions from the audience?
Yeah, maybe me. I have a short question. So thank you very much for this highly interesting presentation.
Thanks.
If I understood you right, you were also evaluating these IV curves with the simulation. And I don't know which slide it was, but this Lambert V function, you used it, right?
Yes, I use the Neldermeet function. Yes.
Yeah. I think that was for solving for the Shockley equation or something. I had one question when you were discussing the different material systems. You mentioned that there might be a toxicity issue with the organic solar cells. What are you exactly referring to, if I may ask?
Yes, sometimes organic matrix involves some toxic materials in the fabrication to improve the dispersion of the matrix.
Yeah, I think you refer to some rather toxic solvents, yeah, so that,
yes,
or let's say an unhealthy solvents. But that, okay, of course, there is quite some development going on to keep these out of the processing, yeah, okay. Yeah, because toxic materials, I connected that rather with some perovskite mixtures that could be more toxic. But if it is about the processing solvents, yeah, one is taking care about that as well. Yeah, thank you.
Thanks. Another question? If not, then I would like to thank the speaker again. And I would like to try again to contact for the next presentation Hadu Al-Ghazi. Is he around? It doesn't look like. Okay. Then maybe I would pass back to Dania.
Yeah. Mm-hmm. So if Mr. He was briefly there, maybe he has connection problems. So what we can do, we just continue with the next session, because I think, yeah, the next session, which is the poster session, the next session number 4, which is the last session of the day, where posters are presented. And this will be moderated by Professor Martin Kamter. Yeah, so Christoph, thank you very much for your moderation, and I thank the 2 presenters of this of your session, Professor Sadok BEN JABRALLAH and Elyes Bel Hadj Jrad. Yeah, so let's just continue so that we can gain time and even close earlier after these 2 days of hard work. So Professor Kamter is our next moderator. He's a professor at the University of Ngaoundéré and the national representative of ANSOLE in Cameroon, and we know each other for a very long time. And he has been a very active member of ANSOLE since the launching in 2011. So, Professor Kamter, you have the floor to present, and I'm happy to see you here on this platform. Although I was in Cameroon, I could not see you.
Okay. Okay. So thank you very much, Professor Daniel, for giving me the floor. I'm very happy to moderate this part of the conference, virtual conference. And so I don't have in front, in my table, I don't have the list of the participants who are going to show us their poster.
Okay, so I can read you the participants, so we'll do it together.
Okay, thank you very much.
So the poster session is meant for 5 minutes. So 3 minutes, 2 minutes, 3 minutes presentation, 2 minutes question and answer. And yeah, each poster presenter can share either few slides or the poster itself. The first poster is from Ibtissem Bousnoubra, which is University of Constantine, Algeria. Removal of.
Hello, everybody. I am here.
Okay, so we can you can share your screen, and she's going to present on removal of Bromocresol Purple by direct photolysis and advanced oxidation processes in homogeneous solution under artificial and solar light.
D'accord. Bonjour à tous. Je me présente, c'est Dr Bousnoubra Ibtissem, enseignante à l'Université Farhat Abbas Assaïd en Algérie. Le travail que je vous présente aujourd'hui a été réalisé au laboratoire de LSTE, laboratoire de sciences et de technologie et de l'environnement à Constantine, où ce travail est axé sur l'élimination d'un polluant organique qui est le bromocresol pourpre. C'est un colorant de modèle par photolyse directe et des procédés d'oxydation avancés en milieu homogène sous une irradiation artificielle et naturelle qui est bien sûr le solaire. La présentation du spectre UV visible de notre substrat choisi, qui est le bromocresol pourpre à pH naturel, montre bien qu'il est constitué de deux bandes d'intensité variable et localisées successivement à 276 nanomètres et une bande principale à 432 nanomètres. Le pH influe sur le comportement de notre substrat qui est le bromocresol pourpre, principalement en milieu basique à pH égal à 11, où nous avons remarqué un déplacement de la bande la plus intense de 432 nanomètres à 588 nanomètres. Dans la deuxième partie de cette présentation, on va étudier la dégradation de notre substrat par photolyse directe à différentes longueurs d'onde et à une lumière solaire. En lumière solaire, d'abord, en lumière artificielle, toutes les expériences de photolyse directe de bromocresol pourpre à pH libre et à différentes longueurs d'onde ont été effectuées en réacteur statique, tubulaire et sous éclairage externe par une lampe germicide émettant un flux photonique incident par la lumière. Par contre, pour la lumière solaire, les solutions à cause du colorant sont dégradées à l'aide d'une installation pilote contenant comparativement à celle naturelle, un réservoir de refoulement, une pompe et un assemblage de tubes en Pyrex. Ils sont proches les uns des autres face à la lumière naturelle. Les résultats montrent que la photolyse du bromocresol pourpre à différentes longueurs d'onde, 254 nanomètres, 365 nanomètres, en monochromatique ou polychromatique, pour la même concentration optimale qui est 25 ppm, 25 mg par litre, est négligeable. Cependant, la photolyse en milieu solaire n'a pas réellement amélioré le rendement d'élimination de ce substrat, ce qui pourrait être attribué au large spectre du système solaire et à une faible absorption du flux photonique incident. Dans la troisième partie, on va toujours étudier l'oxydation de notre substrat par le système H2O2-EV et S2O8-EV séparément. Avant d'étudier l'efficacité de ces procédés à dégrader notre colorant choisi, qui est le bromocresol pourpre, nous avons en premier lieu testé la réactivité de H2O2 et S2O8 sur le BCP à l'obscurité. Les résultats représentent que le BCP est insensible en présence de ces derniers. Par contre, le couplage H2O2-EV et S2O8-EV est nettement plus efficace par rapport à l'obscurité et par rapport que la photolyse directe pour décolorer le BCP, soit à des lampes artificielles ou naturelles plutôt, où le taux de décoloration du BCP augmente en raison d'une grande production de radicaux oxydants qui est les OH point et SO4 point moins. La décoloration du substrat par les deux systèmes mélangés qui est toujours H2O8, S2O8 EV sous une irradiation EV artificielle donne une légère diminution du colorant comparativement à celle obtenue avec H2O2 EV et S2O8 EV séparément. Cette caractéristique peut s'expliquer par une compétition de la lumière émise entre H2O2 et S2O8 qui peut ralentir donc la production des deux radicaux OH point et SO4 point qui sont responsables à la dégradation de notre colorant. Le processus de la minéralisation toujours de notre substrat choisi, qui est le bromocresol par les deux systèmes H2O2 EV et S2O8 EV, séparés ou mélangés, a été suivi par la demande chimique en oxygène, la DCO, où cette dernière a été mesurée en fonction du temps d'irradiation. Il apparaît clairement que ce colorant se minéralise plus lentement que leur décoloration. Ce résultat montre que le PCP n'est pas directement minéralisé, mais plutôt transformé entre produits intermédiaires. À la fin, on peut conclure donc que les performances des systèmes H2O2 EV à 254 nanomètres, S2O8 à 254 nanomètres séparément ou mélangés sont nettement supérieurs à la capacité oxydante du processus de photolyse dans la dégradation du BCP, le bromocresol pourpre. Ainsi, la minéralisation diminue plus lentement que la vitesse de dégradation du bromocresol pourpre par les deux systèmes. Cela pourrait être attribué à la formation des produits intermédiaires. Merci de votre attention.
Merci pour la présentation. Thank you for the presentation, and you kept the time and you were very precise in your presentation. So thank you very much. I don't think is there any person who has a question to her? If not, we will just move to the next presenter. So the next presenter is Hassan Aboudi, University of Mohammed bin Abdullah of Fez. He's going to speak about photovoltaic performance of rectangular and parabolic under applied electric field impact. So the floor is yours. Mr. Hassan Aboudi, are you around? So it seems not to be around, okay?
He's here, but I think there are technical problems, maybe.
Okay. So let's just take the next presentation from Wafia Bukhedena of Tebessa. She's not around, but because she also has a technical problem, but somebody else will present for her. It's Same Boudiba. So Same, can you?
Good afternoon, Daniel. So, hello, ladies and gentlemen. Before starting, I will wish also again. I wish thank ANSOLE organizers for their effort, and for this event, which was very successful. So I will share, I will share the presentation. It is shared. كانش فيها جري. Today I have the honor to present a new synthesized product exhibiting a good corrosion inhibition for carbon steel. Due to its low cost and availability, carbon steel has been extensively used for different purposes in a wide range of industrial applications. However, this material is unfortunately exposed easily to corrosion phenomenon, and thereby it will have a potential adverse effect on the ecological balance and in the economic field, namely in terms of repair, replacement, and product losses. As different organic compounds have been reported to be as effective corrosion inhibitors during acidization in industrial cleaning process. Various organic compounds containing polar functions in their structures as nitrogen and sulfur have been reported as being effective corrosion inhibitor for carbon steel in acidic solutions. As the compounds that contains both nitrogen and sulfur exhibiting high inhibitory efficiency compared to those containing only nitrogen or sulfur. Therefore, in this contribution or in our work, we were interested to synthesize a new compound having a structure presenting this advantage and to study in its presence and in its absence the behavior of carbon steel in 1 molar hydrochloric acid and sulfuric acid aqueous solution. The study has been carried out using weight loss and potentiodynamic polarization measurements at various temperatures. So for 20, 30, and 40 and 15 degrees Celsius. So gravimetric study and potentiodynamic polarization was investigated for this study. As a conclusion, from the obtained results, we can conclude that this new synthesized compound effectively inhibits carbon steel corrosion in both acidic medium, reaching an efficiency of 91.9 and 74.1%. The inhibition efficiency increased with inhibitor concentration at all studied temperature, and the investigated inhibitors is of the mixed type, and its absorption on the surface of steel was spontaneous following Langmuir adsorption isotherms. Thank you for your kind attention.
Thank you, Sameh, for the clear presentation and for the nice results that you have generated. Thank you very much. So is there any question from the audience? If not, let's just continue with the next talk of Ms. Karima Hanini, also from Tebessa University. Effect of ethyl acetate extract of Taxus baccata as an additive in electrode deposition bath. Is Karima Hanini here?
Yes, I'm here.
Okay, then you can present.
It's shared my poster.
Yeah, you can share. Yeah, we are seeing your poster, so you can start speaking.
Yes, hello, ladies and gentlemen. Before starting my presentation, I would like to thank ANSOLE organizer for the efforts provided in this event, and I want to wish it a happy 10th anniversary. Today, I have the honor to present you in this contribution a part of the effort provided by our team in framework of the valorization of the Algerian flora by the evaluation of extracts plant as natural biodegradable products, less expensive and effective inhibitors of the corrosion, and their uses as additive in electroplating baths. In our study, we tested ethyl acetate extract of the plant Taxus baccata as an additive in electroplating bath of mild steel with pure zinc. The efficiency against corrosion of coated specimens was evaluated by potentiodynamic polarization and weight loss measurement in seawater as an aggressive environment. The coating morphology was analyzed using brightness meter, thickness meter, and adhesion test. The first step is that we obtained the Taxus baccata extract from the following chain. The results obtained via potentiodynamic polarization indicate that the presence of different concentration of extract lead to decreased current densities as well as corrosion rates compared to the sample obtained in their absence, indicating that the addition of different concentration of extract in electroplating baths improved the quality of the deposit, producing coatings more resistant to corrosion. The same results in gravimetric method was obtained a better corrosion resistance for plated samples in the presence of different concentration of extracts as additive than those plated in their absence. Regarding the morphology of coated surface and according to regulation ASTM A879, we noted that all measured thickness were in the standard norms. Furthermore, and according to regulation ASTM D 523, the coated surfaces were met. The adhesion test proved that the coated samples surfaces in the presence of different concentration of the extracts are stronger than those coated in their absence. From the obtained results, we conclude that the ethyl acetate extract is a good additive depending on its whiteness and levelness. The plated samples showed a good corrosion resistance in seawater compared with unplated ones. Moreover, those plated in the presence of different concentration of ethyl acetate extract exhibited a higher corrosion resistance than those plated in their absence. Thank you for your kind attention.
I appreciate the fact that you people presented that not only Samuel, but you also presented in English. So it shows that researchers in Tebessa are making a big effort to express themselves in English language, which is the scientific language, so that to communicate at the wider audience. So thank you for well-prepared presentation and for the fact that you kept the time. And so we will just proceed to the last presentation of the day. which comes from Salah Bahar, from BBA, University of BBA, also in Algeria. Yeah, so Mr. Salah Bahar, are you around? Is he around? I don't, let me check. It seems not to be the case. So I think is Mr. Hassan Aboudi already around? If not, I think we are through with the presentation of today. So I have to thank Professor Kamta for your time, although you were not lucky to present the people because you don't have the program in front of you. But thank you for officially moderating the last session of our 10th anniversary celebration. And so we will proceed with just some few time of exchange. And also we'll have to make a final picture, screenshot. Harald, you'll make us once more the screenshot, the last screenshot of those who are still around. So please put on your camera so that we can have our last picture together before we say some words of appreciation and of goodbye. Harald?
Yes.
Yeah, so we let everyone put on his camera so that we should make the last picture today. Yeah.
So I'll wait for another few seconds.
Yeah.
Till Cam's coming.
So please, everyone should put on his camera so that we can. For those who are around, please.
Daniel?
This is Mira? Is Mira?
This is
Yes,
Mira.
Mira, okay.
The daughter of Summer? I'm not seeing you. We are not seeing you people.
The animate, it's not from my side.
Okay.
Ah, okay.
There is a problem. The problem is yours.
Okay. Is it mean that you are the one not seeing you or what?
Hello.
Hello, Mira.
Hello.
Mira, how are you? Comment ça va?
I'm fine.
Ah, oh, you speak English?
I'm fine. I'm fine. I'm Samir.
Hi, Mira. Hi, Mira.
Hello.
Can you put the camera?
I had a problem, Samir. It's not mine because I want to open it, but it says that the animator doesn't open it. I'm Samir.
Okay, let's try to make this thing quickly so that we should gain time. If everybody has his camera on, then Harald, please do the last.
Daniel, can you put my name on my picture? Please. Okay. Thank you.
You cannot put.
I cannot. I have. I cannot do it from my computer. now.
So what's your name? I just do it.
Yeah, she's called Louisa Boudiba. Louisa,
Louis.
L-O-U-I-Z-A. L-O-U-I-Z-A. Boudiba, B-O-U. She was a moderator yesterday of the posters, the moderator of posters yesterday. Louisa Boudiba, Professor Louisa Boudiba.
Oh, that's fine. Okay, screenshot is.
Thank you very much.
We can see here now, Mira.
Okay, let's make the screenshot now.
Okay.
Everybody on? Yeah, then go ahead. Smile. Just wait. Reinhold is coming in also. The last session. The last.
هي وليزا مع بعضهم نفس البلاصة.
Okay, then now Reinhold, are you already?
Yes. Good afternoon.
Yeah, we are making now the last. We have True.
Oh, okay.
The last photo. Then we can have some last words appreciation before we leave. Summer, can you put off your this just the microphone first so that Summer, can you put off your microphone just for a short while so that we Harald, you do the screenshot.
Just have a look.
It is off, Daniel.
Okay, yeah, you are now on. Okay, so that's good. So we do quickly because Summer is on. So yes.
Of Daniel?
Yeah.
I can't.
No, we are still.
So the screenshot is shared.
You shared it here. Okay, so we can take it also. So I think thank you. Can there's a lot of is Mira around you? There's a lot of children noise. Can we put whoever? Yeah. So we've got to this point, and I will allow some of you to say some few words before we close. We have, I think, let's say 30 more minutes or so together before we separate. So before I say the last, okay, we have 31 more minutes together.
Daniel.
Yeah.
Thank you very much. This is Ahmed Hanashi from Tunisia, south of Tunisia. Thank you for the invitation. I'm so sorry because I'm going to leave. Probably I can catch you later, but I wanted to say thank you very much one more time. Happy birthday. And I'll be glad, I'll discuss that with Samir, to join the gathering of African friends and European friends and South American friends and all over the world. Okay? Yeah. Was very, very pleased with the invitation and following the nice presentation, nice talks. And thank you very much one more time.
Thank you for you.
Bye-bye, Samir. We'll talk
Bye-bye.
to you. I don't have your phone, so I'll try to call you.
Okay, thank you.
Okay.
So I said that the floor is open for people to talk now before we have the 30 minutes to do what we have to say before we close.
Okay, I have something to say. Do you?
Yeah, you can speak.
Okay, thank you very much. Just to say, very, very happy for this birthday of ANSOLE. And I'm very, very happy to participate and to see one time more Professor Daniel, Professor Samir. Hello, Professor Samir. It's very, very interesting.
Hello.
Yeah.
I'm happy to see you.
Yes, I'm very, very happy to see you.
Thank you.
We were meet in Bajun on by
2 years later, no?
3 years later.
3 years later.
Yeah. 3 years later, yes.
Yeah, okay.
Okay, very, very happy to see you again.
Thank you. Me too.
Okay, yeah, thank you. Okay.
We hope we can organize something else in Cameroon.
Yeah, I hope. Yes, yes, I hope. I'm waiting for you.
Thank you. Okay.
Okay, thank you.
Now in Tunisia, all events are prohibited due to the COVID. But Daniel tells me that it is possible to do any events in Cameroon.
Yeah, everything.
Yes.
That's already restriction.
Even in Boya. Even in Boya. We have a meeting in Boya this year.
Okay.
Yeah. And we hope we will be there. We will be together.
Oh, I hope. Okay.
Okay. Thank you very much.
Thank you for you.
So Aledium, do you want to say something? Professor Reinhold, do you want to say something? And yeah, you have the possibility of saying some last few words before we separate.
Well, first of all, I'd like to thank you, Daniel, for organizing this event and putting so much effort into it that it could happen. By the response of a great many of the participants, I realized that there's extremely positive response to it. And I think an anniversary, like a 10-year anniversary, deserves to be celebrated. And it was worth the effort from my perspective. As far as the conference is concerned, I think you put together a very interesting program. And most of all, I think it was extremely valuable also for us, although I couldn't participate in everything. But as far as I was involved, it was definitely great to get into some further interaction with all of you. Meanwhile, I found my book by Fritz Schumacher, Small is Beautiful, also, since this was a discussion point in the morning session. And it's probably a good idea once in a while to go back into the previous literature. So all in all, I'm very, very happy that this event happened. And I'm, like I mentioned this morning already, I'm very much committed and also to a certain extent optimistic that the work together will continue and hopefully provide results in the interest of the African continent, in the interest of Europe, and in the interest of the world at the end. So
thank you
happy
very much.
anniversary again, and good luck to everybody. I'm just looking into the group, and I feel sorry, Ineke. I mean, we had great time in Africa. We didn't get around to get into a hopefully in the not too distant future, there will be again a physical meeting, because although these things seem to work, I have to admit, perhaps on a personal note, maybe, and then I finish off and pass on to other people. On a personal note, I'm very much aware that at least I and many of the people that I know belong to a very, very, very privileged class of people, even in these difficult COVID-19 times. Nevertheless, I started to realize I'm spending so much time in front of this camera here, and much of the time is, originally it was fun for the first few, say, weeks and months. We all tried to learn, but more recently, I find I'm getting more and more tired of it. And I do hope very much that there will be, in the not too distant future, occasions where we can meet physically again and have a beer or a glass of wine, or maybe just a coffee or a glass of tea. So good luck to you all, and stay healthy, everybody.
Thank you very much. Once more, I want to thank you for your input, your support, and since, as I said, since 5 years that we met each other by God's grace, and we've been working together. We've been to Africa together. We've had wonderful time, and I'm so grateful that you, IPME, and yourself, you've supported not only the part, but you supported this meeting, particularly this 10th anniversary. Thank you very much, Reinhold. Yeah, thank you. So I will pass the word to Ineke. Yeah, Ineke, that Reinhold mentioned you, so you have the possibility to say some few last words before we go.
Oh, well, I think it's great that ANSOLE now celebrates its 10th anniversary, and it's grown immensely. Like you said, there are over 1,100 members already, and yeah, I think it's a great platform for networking, for establishing contacts, for discussing work. So yeah, I really hope that there will be future opportunities to meet live and discuss new projects. I also hope this connection with ISP is going to be fruitful, so a lot of people can travel and get experience also in other labs. So yeah, so keep up the good work.
Thank you, Ineke. Thank you for being faithful to ANSOLE since we met 2012 in that was St. Petersburg, I think. Was it St. Petersburg?
Yeah, I think that's where we met, yes.
It was St. Petersburg. That's where we met then. Yeah. And since then, you joined ANSOLE, and you've been very faithful to ANSOLE, representing us, trying. We tried in the past to write EU project. It did not succeed, but yeah, we tried. So thank you very much, Ineke, for having you as a faithful person. And yeah, and as you said, I'm happy that ISP is open for discussion for us to see what ICTP was doing in the past. If ISP can take over, that would be wonderful for our network. So I want to give the word to Amel Ben Fred. Amel, Professor Amel, are you there?
Maybe her microphone doesn't work.
Just the mic.
Can you hear me?
Yeah, we hear you.
It's okay. I would like to thank once again all the invited speakers and all participants. A great thanks to Professor Sarshifci, who helped us and opened the door to our students As you know, Moufid was in Linz, Mohamed Amin, Mariam, Umayma. These students have defended their thesis thanks to this collaboration with the Linz Institute. This collaboration was supported also by our friend Daniel, who gives us polymers on which we have done good papers. Thanks, Daniel. We are happy to have you as friend. Once again, happy birthday to ANSOLE. And as it was said yesterday, without your energy and your enthusiasm, ANSOLE will not be a reality, and we will not be here to celebrate its 10th anniversary. Thank you, Daniel.
For the nice word, and yeah, thank you very much. Yeah, for the nice word, really. But I want to say, you and Samir, you played your role. You've been from the beginning. Us not only faithful friends, we are now collaborators. We've published a lot of paper together. As I said, I came to your home. I've eaten with you people. We are family. You've been to Cameroon. We've been to Arusha. We've been to, I don't know, places together. So it's, yeah, ANSOLE is a big family. And I hope this family will grow more and more with the younger generation coming up. Thank you very much. So is Elif, are you around? I think Elif is not around. Okay.
She's there, but she is muted. So
it's muted. Maybe.
Your microphone, Elif.
Sorry, I forgot. Yes. Daniel, the question, sorry, is it now ANSOLE or ANSOLE? Can we decide it now in this 10th of anniversary?
Just as call what you want.
Okay. Yeah, what should I say? I mean, of course, I like this committee very much. This is, I have a great sympathy of this idea, bringing the cultures together to work together. And Daniel, I think you did a good job. And I hope we will make the next 10 years together also.
Yeah, thank you. That's a good thing. That's good for yeah. So, yeah. So Luisa, is Luisa around?
Yeah, I'm here.
Okay.
Good afternoon. I want to thank Daniel for all his efforts to helping students all in Africa. And I want to say something. Professor Lang said if you have suggestions to give to help the students, you can give them. So I propose to help our students to go to the European laboratories to do their experimental work. And if it is possible to help them by sending them invitations. We will thank all professors who want to help us for that, because we have some problems in Algeria. We haven't all the instruments necessary to do our research. So going to Europe to do that will be a great opportunity for us to give something to science. Thank you very much another time. Thank you.
Thank you, Luisa. So Luisa, you were in the SUS meeting where we started everything, although you did not participate. during that 9 people, okay, was
Yeah.
but we were there from the beginning, and since then we've shared a lot. And yeah, you sent your sister who came to Linz and was one of the first students who benefited of
Of a grant, yeah. Thank you very much.
Yeah. So I want to give the word to Summer, if she's there, to say some few things.
She's here, yeah.
So Summer, you have I say you were the second student who benefited from us. The first student is Penny Duvalier, a Cameroonian student, but I don't know whether he's also here. But Summer.
Thank you, Daniel. Thank you for giving me this opportunity, which I want to use to thank ANSOLE again, because without ANSOLE, I will never be an assistant professor. So it gives me the opportunity to learn a lot, to do a lot, a nice paper, to meet many peoples, and to learn in my life a lot of things. So I hope it will continue to help students to do their research, to finish and to complete their curriculum in their life. We are here to help ANSOLE, to continue to help ANSOLE, and if we can, for sure. So thank you for everybody, and thank you again for ANSOLE and for Daniel.
Thank you, Same, that you came to our lab. You had not learned a lot, but you were so let me say, so intelligent to catch up very fast. And in synthesis, because before coming to my lab, I remember when she came, to say the truth, this is something I'm revealing, she was crying. She said she wants to go back because she cannot go. But I said, calm down. And then we say, we can do it together. And she became the teacher of others. And the good thing was that through her, another Algerian student came from Bijaya who learned from her and also finished her PhD. She's now in Canada. So you see, you were very hardworking. I'm proud. And you taught me a lesson that you should never undermine a student, and especially for African students who do not have the opportunity at home to have some experimental, practical experience in the lab, to give them an opportunity. And you showed it that if they give you the opportunity, you can learn fast and meet the high level, because we publish very good papers, very high level papers. And the same thing you taught Nasima, who came from Bijaya. So she also learned fast, and we also published good papers. She couldn't finish her PhD. So it was a good lesson that I learned from you people. And Professor Lang can confess, because in many situations, I tell him, give the opportunity. And I think give the opportunity to the students, even if their CV is not so good, because and most CVs from Africa are not comparable to the European students. The European students have all the facilities, but most of the African students who are coming to Europe, they have this desire to excel. They said, I have the opportunity, I want to use it. And Safa Azu from Morocco proved to us within 2 months, she got the result that helped her to finish her PhD, which also helped us to have a Nature photonic paper. So one can really see that give the opportunity to African students, those who are really motivated, they will excel. And but I'm still saying, instead of us always thinking of sending all our students to Europe, let our governments, let the African government do something and put in money in research and development, equip our labs. Then that will also create good collaboration between Europe and Africa, so that students from Europe can come to African lab and vice versa, and good exchange will take place. And I think that should be the objective in the future, not only thinking of sending the student to Europe and doing nothing to equip our labs. Our labs should be equipped. So I think we should, the discussion that we are going to have, which I'm planning with Professor Lang and Ineke and others, this EU-Africa relationship at eye level. So those are things that we want to discuss and see what we can do. Yeah. So who else? Moufid, are you around? Do you want to say something? And Harald, you can say something. You've as a member of ANSOL from the for a long time also. So the floor is open to others to say something before Samir will speak, and I will speak last. I think, yeah. Alejium, he's just coming in. Mm-hmm.
I'm jumping into the break. So no, sorry.
Hello, Daniel.
Yeah.
Do you hear me?
Yeah, you can hear. So you have the opportunity to say some few words of before we close this our 10th anniversary event. So
the few words I have to tell today is just thank you very much for all your effort you devoted to help young African researchers and to foster them, and to try to find out how the different possibility to offer possibilities to do experimental abroad, because we know in Africa we have so many problems to get to equipment and to do experiment. And I cannot say tell enough thanks to ANSOL and all ANSOL, because I get my first postdoc through the ANSOL program in Morocco, and then it's with the same network I get opportunity to have the trial program of ISTP, and right now I'm assistant professor in Senegal, and recently I'm promoting to be to handle so many administrative all the technopedagogical office I did here, and I think so the experience I get through the different program of ANSOL, I cannot tell so many things for this. And I, by the way, I thanks also Harald Hoppe, who hosted me in Jena for 3 months, and I discovered so many things in experience, particularly in polymers for PV application, and in the same way to Alam, Shahidul Alam, who hosted me in house chair with me the same office in Jena. And I never say enough thanks to Daniel particularly, because he come in Senegal and he know what we live in Senegal, the different problem we meet to do normally our researchers, and he devoted so many efforts to help us. Thank you very much, Daniel. And just to say, I still answer, and I be answer and still answer, and answer forever. And thank you very much for all.
Thank you for the nice words, Aledium. I'm very proud that you have a very senior position now at Tebessa University, one of the, I can say, one of the best universities in West Africa, in French, especially in French-speaking Africa, and seeing our fellows taking leadership position gives me a great joy, and this is why we are here to to build up leadership, the future leaders of our continent. If within this network, you will gain knowledge and you will be a true leader. Yeah, so thank you for the nice words. So,
and thank you for your appointment letter. The new mission you give me in Senegal as Senegal.
Yeah, you are the national representative of ANSOLE
Thank you very much.
In Senegal, yeah. So I think, are there other ANSOLE members? Is Shema around, or those who've, Shema?
Yes, I am here, Daniel.
So the floor is yours.
So can you hear me?
Yeah, we hear you.
Okay. Okay. I also want to say thank you for all of you. Actually, it was throughout these 2 days, I was very happy to see all of the people. I miss all of you. So you are like my family, my international family. So I was very happy to see most of you. I missed you during these 2 or 3 years. We couldn't see each other because of this pandemic. But thank you, Daniel. Thank you, Professor Samir and Dr. Amel for giving us the opportunity to meet even online. And I hope that next time we can meet physically together and come back to our annual meeting and always meet in physical. Thank you for the ANSOL, of course, and for all the people. I was also happy to see Professor Sarasevci, Dr. Harald, Hoppe, and Christoph, all these people who I missed during all of the previous time. And I would like to congratulate you for this successful event. It was really interesting, a lot of very interesting talk. And I wish you the more and more success, and that the ANSOL growing more and more. Thank you very much.
Thank you, Shema. Shema is also one of our students, and I said it also yesterday that I'm proud that she benefited from our scholarship. She came to Elyes and did 2 years, and she could complete her PhD, and now she's also assistant professor at the University of Science and Technology. She represents ANSOL in Egypt, and she was the one who organized the 5th anniversary. So the time passes very fast, but I'm happy that she's with us today. Although she told me that you lost your auntie yesterday, but our condolences. But we are very happy to have you in this big ANSOL family. So I think I hope that all. Let me see. Is Malik Maza around? Or he has gone already? Okay. So there are no more. Harald, do you want to say something?
Yeah, okay, then I keep it really short. I was very happy to be part of it and to see you all again. And yeah, hopefully soon in person. And yeah, thank you again for this organization. It was really nice to see you again.
Thank you. Okay. So I want to say that Harald has played a big role in capacity building of African students. I want to mention that. So many students went to your lab, not only Ale Diom or Shema who came as a postdoc. We had Adam Getachew. We have so many students from Nigeria, and there are some now even in your lab, around 3 or 4 African students from Ethiopia, Nigeria, and elsewhere. Thank you for your contribution in capacity building for Africa. So we know each other since 2003. We've published together. You are my junior brother, let me put it this way. And so thank you for your contribution as an ANSOL member. You are one of the founders of ANSOL EV, the NGO. So you've played a big role in our activities. Thank you very much, Harald. So I think, so I can pass the word to Samir. Passing the word to Samir, I want to thank him. He was the one who actually was to organize the meeting in Tunisia. He did a lot of work before I took over because of the Corona issue. And I want to thank him and Professor Sherif Dridi and the son of Samir and Amel Benfred, who was the webmaster for the conference, and they did a lot of work, but the Corona always come and cross everything. But however, I think that everything has worked for our good, as the Bible says, that we had this format and we could meet many people, having people coming from Mexico, like Maria Teresa, who attended virtually from Texas, from India, and also having Professor Lang and Professor Sarisifcha attending. They will have not normally, even if there was no lockdown, most of them will have not traveled because of other duties and other issues. So we are happy that you took everything and started everything before I took over these last 2-3 days to make this event a big success. Really, I'm so proud that it's a big success. I want to thank Samir for the fact that what I said already, since we met each other in 2010, we've gone these 10 years, more than 10 years together in different form, with exchange of materials for this, and many of his students coming to while I was in Elyes, coming to our lab in Elyes to do experimental work, and we've published also a quite number of papers together, which is also the essence of such a network. So thank you, and thank you, Samir. And I think that you still have some of my material, many of the materials that, and you've put some students on them, and you've still asked me to send you some material. So I think the collaboration will continue so long as God gives us air to breathe and to give us life. So I'm so happy to have you as my friend and brother. We are born in the same year. We have the same sign. We are Taurus, yeah. Born 1966. He was born 24th of April. I was born 20th of May. So we're almost like twin brother. Let me put it this way. So Samir, you have the word.
Thank you, Daniel, for the nice words. Donc, just for first, we planned to organize this conference at SUS and inviting some founding member of ANSOLE, but due to the pandemic, though, it is impossible to do this at Tunisia. So I think I really thank you, Daniel, for the great effort that you've done to push us to do this 2 days. So without you, donc, the days were delayed. I want to remember you, Daniel, for the first ANSOLE Day in Cameroon, Yaoundé, in 2012. The amphitheater was full, and the students were standing to follow the conf. I think that is more than 200 students. This conference, I remember that that was Ralph, you, me, Louisa, and Zuhair, and we spent.
Harald was also there.
Harald also, and Nadia Kamayoni, but now that is not here. I think that this was the declic for me. The days in Cameroon, we spent really beautiful days, and this encouraged me to spend more time to ANSOLE and its activities.
Yeah, thank you.
And we hope that the energy will continue, and ANSOLE can help other students for the future.
Yeah,
but I know that now ANSOLE haven't much money without the ICTP funds. So I think that we can continue to organize such conferences. And I think that we will continue also with the schools, with the small workshops, And if we can have the technical opportunity to do it remotely, I think that it will help more students in Africa. And I answer again, I hope to ANSOLE happy birthday, and we hope that we can continue with you and with ANSOLers. And thank you also, Daniel.
Yeah, thank you very much, Amir. I want just to pick up what you said. You suggested that already yesterday. And Professor Lang, you are here. I hope that you've not gone already. Samir was saying that in cooperation with IPME or JKU, we can do some also, if during this pandemic period, have some schools where students can come together online. And with the technical support that we had, just like this one, we could do a series of things. So I hope if Harald Kika, who has been very supportive, and Reinhold, you accept this concept that all those schools will be in cooperation with IPME or JKU. Reinhold, are you around still, or you've left already?
No, I'm here.
Yeah, so I was saying, Samir suggested that we should.
I heard it. Yes.
Yeah. So we're asking if you give your blessing.
Yeah. Well, let's discuss it. In principle, you know, I'm very open to any activity of this kind.
It would be more or less at online activities supported by JKU, where we can do different schools, or where students just come and because you know you could realize that there was a lot of, just within the short period of time, a lot of abstract coming from students from some countries, especially Algeria, and I'm not want to diminish the Algerian society, but most of the students there do not have the opportunity to travel abroad to attend international conferences. So this is a wonderful means for them to attend and present. Very important for their CV, very important for them to complete their PhD thesis and so on. So I remember 2015 with Zahir at the University of Bordeaux, Arigit, BBE. We organized such an event at very short notice, and we had more than 400 registration for a very short time, because the students said this is an opportunity for us to attend and have at least accomplished certain requirement for our PhD. So if we can offer such things online, now that because of the pandemic, and if you have a good technical support, this is going to be a good service to many African students. And so let's, and I think this is something that if the support of JKU is there, it strengthening JKU international relation to Africa. So let me put it that way. Yeah. Okay. So I will now, I'll just say, I want to thank everybody. So I want to make the last words, thank everybody for coming. It has been for me hard, let me say how many days of hard working, putting the things together. And I'm very proud. I'm very proud. Yesterday I was so happy. And I'm also very happy today that we are celebrating, we succeeded to celebrate this 4th anniversary and on time, and that we did not postpone it. So, and I thank all our sponsors. I thank ISP, I thank IPME of JKU. I thank Carla, I thank Reinhold, I thank Samir and Amel, and I thank Ineke, I thank Maria Teresa, I thank the moderators and the students who participated, those who gave the lectures, but I'm extremely happy that we've gone through these 2 days, and that we've achieved a lot in the past 10 years. So, and I cannot list everything. Like just for example, now we are even offering dancing, and so has so many aspects. But for the society here, because of pandemic, where we were forced to do open air dance event, which has been taken off by the city. They found it very, very interesting. They said this is one of the best cultural events. So ANSOLE is so multifarious, and so I'm so happy that we've gone through these 10 years together. And I thank those who helped me at the beginning, who helped me in the middle, who supported me when things went rough, and who are still supporting. And I think for me, I want to say my biggest joy, or let me say, was to meet Reinhold, who has been professing sustainability for a long time. When I got to Linz, I read about him, but okay, I was not somebody who would go and knock at the door. I'm here. So by chance, we met at Freiburg in 2016 at the famous macromolecular symposium for polymer chemists in Germany. This is the address to, there's a conference to attend. And I had not attended the conference for almost 3 or 4 years, but that year I went, and he was giving his talk on water, energy, sustainability, and then I approached him. And so we are the only 2 Austrians, let me say, and then I said, I enjoyed this talk. He said, oh, come to when you are in Linz, come to my office. And I talked about ANSOLE. So he said, come and present. I went and presented ANSOLE. So he just loved the idea, and that's how we started. And then BALEWARE came in, he embraced it, and how God did things, we are today where we are, and I'm so grateful for knowing you and that you are supporting me, and I think as God gives us life, we have more to do, and I said we have this discussion which I'm inviting some of us here to a relaxed online exchange on EU-Africa relationship. And as I was saying today, we are getting to the new normal where the Africans are regaining their self-esteem, especially I will not only say Black Africa, also North Africa, because the same situation of disparity between Europe and Africa in general, it has nothing to do with just sub-Saharan Africa. Also in North Africa, we have that disparity where those coming from Europe dominate and so on. So we have to discuss. We have to sit and start talking and see how things can change. We have to start the change at our level. Maybe it might take 30 more years before there's real cooperation at eye level, but somewhere it has to start, and we can start. And I'm seeing the momentum. I'm seeing there's something. There's the energy for that, and we have the right people in our network, and so we can start that discussion. So I will just say the conference would end today, but there's still something to do. I will need, for those who could not send their biographies, I have to prepare a conference book that you will receive. We'll put some pictures. The screenshot will go into that book, and then we'll make a nice thing that for the memory of this 10th anniversary. So you expect some emails from me, to get some information from you, and in the nearest future. I think Reinhold, your biography was the old biography that I took for 3 years ago. So maybe you have new biography and new pictures. So I will ask you also to send me a biography and other people here. So, and those who, so I'm going to send emails because there are going to be some certificate for those who pay the 30 euro, which we ask for. So you expect some emails from me the next week. I'm so tired, to say the truth. But I'm going to sleep very well today after this 2 days of hard working, and I'm so happy that we've got to this point, and we have much to do. That's why we are living.
Daniel?
And then so Badadi. But that you just appeared.
After you, if you like.
Yeah.
say only 2 or 3 words, if you like.
No, yes, I did not know that
If
you
you
were
give me
around.
the time, please.
Because I'm sorry. So you can speak.
I am. Thank you very much. Thank you. I am so sorry for not being the 2 days of this interesting meeting, because I was, as I said yesterday, I am involved in mandatory tasks, because yesterday I was speaking from Rabat because of the examination. I am completely focused on the examination, and now I am speaking with you from Fez, because I was traveling today from Rabat to Fez because of my involvement in the panel of. So this is why I didn't have the time to attend and to follow all the scientific sessions, but she was participating, and she gave a talk in this scientific meeting. All. Do you hear me? Do you hear me? I don't know whether you hear me or not, because the connection is not very well.
Somebody's microphone. Some people.
No, selectionnel.
Aledium, can you put off your microphone, please? Aledium,
yeah.
Put off your microphone. There are people worrying behind.
Okay, sorry for this trouble. So I would like to say only congratulate all. Congratulate you first, Daniel, for the success of this international scientific meeting, and would like to say thank you for all my friends, Samir, Amel, Shaima, everybody who participated in this meeting. Few minutes before, you were speaking about Safa and the Safa Moroccan fellow. Do you know? Do you remember? Of course you remember.
Yeah.
So I would like to say that Safa is now one of my colleagues in the University of Mohammed V in Rabat. She is now assistant professor at Faculty of Science, which is part of the same university, minus at home university. So we are colleagues, and we are both involved in master of excellency on renewable energy and batteries. And I would like to say, at a home university, we have now an excellent platform for experimental works on many kinds of PV systems. So this platform is open for all ANSOLers, all students, all young researchers. So if somebody would like to come and to perform some experimental works at this solar energy systems platform, he will be welcome, and we will be pleasant to receive and to perform together with him some interesting work. I would like to say also that what I would like to say. No, I said everything. I would like to congratulate you once more, and thank all the members of the organization committee. And I hope we will have the chance to meet physically and to participate in the next edition of ANSOLE Days. Thank you very much, Daniel.
Thank you, Abdel Fattah. As I said, Abdel Fattah is also one of the founding members, already from SUS. The 9 people who met in the night of the 4th of November, you were one of them, and you came to Linz for the launching also of ANSOLE, and you represent us. You are the vice regional representative of ANSOLE in North Africa. So, and we signed an MOU with your institution, École Normale Supérieure de Rabat. So we have a lot, and I'm very proud that Safa is now your collaborator. This is one of the fellows who came to our lab and did work within 2 months and had very good results. And so she would have been here, but she told me that she was sick. So, but I'm proud that you have such a good lab, and I will make this information known to many African students who are looking for experimental facilities to conduct their research. So thank you for the good information and your readiness to receive a student in your lab. So thank you very much. So, and I hope that I've not left any person, because I'm not seeing all those who are in the list now, but you are one of one of the most important people of as founder of ANSOLE. You deserve to say something. I'm sorry that I was not aware that you are already in. So I would just say I want to thank everybody for attending, and you hear from me, and let's keep this momentum, and so have a blessed weekend, and thank you very much for coming. Once more, happy birthday, 10th anniversary birthday to ANSOLE. So I'll just say goodbye, and
goodbye.
I love you all. Okay.
Thank you. Goodbye.
Okay.
Thank you very much, Daniel. Thank you. Thank you, all of us.
So I will not forget to go without thanking Harald. We have to give a clap to Harald. I don't know where you are. Harald Kika for Harald Kika, not Harald Hoppe. Harald Kika.
Yes, for Harald Kika.
Thank you, Harald Kika, for.
He does a very good job. Very professional job.
And for the wonderful job that you did these 2 days. Thank you. Harald, I thank you also, but this club goes to Harald.
Yeah, it was a very organized meeting. Thank you very much.
Okay then, bye. So
Thank you, bye.
Bye.
Have a nice weekend.